Racing through the silent void, a crimson beacon in our night sky, Mars has always captivated humanity. We see a desolate world, a barren landscape scarred by ancient impacts, swept by dust storms, its thin atmosphere incapable of sustaining liquid water. For decades, we've gazed upon its rust-colored plains and towering volcanoes, believing we understood its story. A planet that once held the promise of life, now merely a frozen echo. But what if the silence is a deception? What if beneath those ochre sands, buried beneath billions of years of cosmic dust, lies the impossible truth of a forgotten civilization? Tonight, on Tierra Hueca, we embark on a journey that challenges our deepest assumptions. We will explore the subtle anomalies, the tantalizing glimpses, and the perplexing questions that whisper of a past far grander and far more enigmatic than we dare to imagine. Prepare to gaze upon Mars not just as a planet, but as a cosmic riddle, inviting us to wonder, did someone once call this red world home? Racing through the silent void, a crimson beacon in our night sky, Mars has always captivated humanity. We see a desolate world, a barren landscape scarred by ancient impacts, swept by dust storms, its thin atmosphere incapable of sustaining liquid water. For decades, we've gazed upon its rust-colored plains and towering volcanoes, believing we understood its story. A planet that once held the promise of life, now merely a frozen echo. But what if the silence is a deception? What if beneath those ochre sands, buried beneath billions of years of cosmic dust, lies the impossible truth of a forgotten civilization? Tonight, on Tierra Hueca, we embark on a journey that challenges our deepest assumptions. We will explore the subtle anomalies, the tantalizing glimpses, and the perplexing questions that whisper of a past far grander and far more enigmatic than we dare to imagine. Prepare to gaze upon Mars not just as a planet, but as a cosmic riddle, inviting us to wonder, did someone once call this red world home? But let us not be fooled by the profound desolation we see today. The red dust of Mars is not a static shroud, but a veil concealing a much grander, more vibrant history. To understand this planet's deepest secrets, we must perform an act of cosmic imagination and travel back in time, to a period when Mars was not a red desert, but a world of blue. For planetary scientists, the evidence is now overwhelming that early Mars was a much warmer, wetter, and more dynamic place. It's a key part of the larger story of the planet, and the very foundation of the search for past life. The signs are not subtle. They are etched into the planet's very surface. Satellite imagery and rover exploration have revealed unmistakable ancient riverbeds and valley networks which wind across the landscape in patterns that could only have been carved by persistent, flowing water. These channels often branch out, forming vast, intricate systems, some of them hundreds of miles long, leading into what appear to be ancient lake beds and deltas. One of the most striking examples is the massive outflow channels that once drained colossal lakes, a testament to floods on a scale unimaginable on Earth. Our robotic emissaries on the surface have confirmed these orbital observations with startling detail. The Curiosity rover, exploring Gale Crater, found itself driving over sedimentary rock layers, the kind of layers that only form at the bottom of a lake. It discovered hydrated minerals, such as clays and sulfates, which are a direct chemical fingerprint of long-term interaction with liquid water. The Perseverance rover in the Jezero crater is currently exploring what scientists believe was a large ancient lake that hosted a river delta, an ideal environment for preserving evidence of past life. The very purpose of its mission is to collect these samples, which act as a geologic time capsule of Mars's watery past, for a future return to Earth. This leads us to the second, and equally crucial, piece of the puzzle, a thicker atmosphere. For liquid water to exist on the surface of Mars, the atmospheric pressure would have needed to be much higher to prevent it from simply boiling away into space. Scientists believe that this early atmosphere was composed primarily of carbon dioxide, which would have created a potent greenhouse effect, trapping heat and allowing the planet to be warm enough for water to flow. The process of this atmosphere's demise is a story in itself. The Mars Atmosphere and Volatile Evolution MAVEN mission has provided direct evidence of how this atmosphere was lost, showing that the solar wind stripped it away over billions of years, a process called sputtering. This atmospheric loss was accelerated by the planet's lack of a global magnetic field. Unlike Earth's, Mars's magnetic dynamo died early in its history, leaving the atmosphere exposed to the sun's harsh particles, which slowly but relentlessly eroded it away, molecule by molecule. We even have a precise, albeit chilling, record of this loss. Scientists have analyzed the ratio of hydrogen isotopes in the Martian atmosphere. Light hydrogen, being more nimble, is more easily lost to space than its heavier counterpart. The fact that Mars's atmosphere today is enriched with the heavier hydrogen isotope confirms that a vast amount of water, which is made of hydrogen and oxygen, has been lost to space over time. This isotopic signature is a final quantitative nail in the coffin of the old, warm Mars. The collective evidence from surface geology, mineralogy, and atmospheric science paints a picture of a planet that was once a very different place. It was a world of rivers, lakes, and perhaps even oceans, with a climate that could have been hospitable to life. It was a blue world, and for a period in its history, spanning hundreds of millions or even a billion years, Mars could have been a planet alive. The question that lingers, however, is not whether Mars was once wet, but what, if anything, lived in all that water. A closer look at Mars reveals compelling evidence that its early, watery past included vast, standing bodies of water that could only be described as oceans. While the existence of rivers and lakes is now widely accepted, the presence of a global ocean has been more controversial. However, recent discoveries have bolstered the argument. Significantly, the most direct evidence comes from what appear to be ancient paleo shorelines that demarcate a clear boundary between the smooth northern lowlands and the cratered southern highlands. These immense horizontal boundaries, stretching for thousands of kilometers, suggest that a massive body of water once filled the northern hemisphere. For decades, scientists debated this due to a major challenge. The supposed shorelines varied in elevation by several kilometers, which is inconsistent with what you'd expect from a standing body of water. However, some researchers now believe this variation can be explained by geological processes that occurred after the water receded, such as true polar wander, where the planet's axis of rotation shifted, or the immense weight of volcanic regions like Tharsis, warping the planet's crust, further solidifying the ocean. Hypotheses are the discoveries of thick sedimentary deposits that point to a long-lived body of water. China's Zhurong rover detected extensive dipping deposits beneath the surface of Utopia Planitia using ground-penetrating radar. These layers, tilted at an angle consistent with what is seen in coastal deposits on Earth, provide strong subsurface evidence of an ancient shoreline. The thickness and length of these deposits suggest a long-lived ocean with wave action rather than a short-lived melt event. Beyond topography, mineralogical evidence supports the ocean theory. Researchers have identified large-scale deposits of minerals like talc and serpentine in the Eridania basin of southern Mars. These minerals are typically formed on Earth by hydrothermal activity on the seafloor, where hot, mineral-rich water erupts from volcanic vents. The sheer scale of these deposits suggests a long-standing deep-water environment, with some estimates proposing this ancient sea held 9 times the volume of North America's Great Lakes combined. This finding is particularly significant because it points to a potential cradle of life, as similar environments on early Earth are thought to be where life first emerged. Finally, intriguing evidence comes from the possibility of ancient Martian tsunamis. Scientists have identified huge boulder fields and unique erosional patterns in the northern plains that can't be easily explained by wind or river action. One compelling theory suggests these features are the result of catastrophic tsunamis triggered by large asteroid impacts into a northern ocean. The distinct patterns left behind, including the size and distribution of boulders, match those seen on Earth after massive tsunamis, providing a powerful, albeit indirect, argument for a long-gone ocean. The Great Drying of Mars was a slow but inexorable process, driven by a series of interconnected events that ultimately transformed the planet from a potentially habitable world to a cold, dry desert. The most widely accepted theory points to the loss of Mars's global magnetic field as the catastrophic turning point. Earth is protected from the sun's harsh radiation by a powerful, internally generated magnetic field, a force field known as the magnetosphere. It's created by the motion of molten iron in our planet's core, an effect called a dynamo. Early Mars, with its own molten core, had a similar dynamo and a protective magnetic field. Evidence for this ancient magnetosphere is locked in the planet's southern highlands, where rocks show alternating bands of residual magnetism, a fossilized record of a magnetic field that was active billions of years ago. However, because Mars is much smaller than Earth, its core cooled and solidified much faster. This cooling caused the dynamo to cease, and around 4.2 billion years ago, Mars's global magnetic field died. This single event left the planet's atmosphere exposed and vulnerable. With its magnetic shield gone, Mars was at the mercy of the sun's solar wind, a constant stream of high-energy charged particles. This powerful current began to directly bombard the planet's upper atmosphere, in a process known as atmospheric sputtering. This phenomenon works like a cosmic sandblaster, where charged particles from the sun slam into atmospheric molecules, knocking them free and accelerating them into space. NASA's MAVEN, Mars Atmosphere and Volatile Evolution spacecraft has been observing this process in real time, providing direct evidence of how the atmosphere is slowly but continuously being stripped away. While the current rate of loss is small, it was much more rapid billions of years ago when the sun was younger and more active. MAVEN's data has confirmed that most of the gas ever present in the Martian atmosphere, including water and carbon dioxide, has been lost to this process. Atmospheric stripping was not the only mechanism at play. On a global scale, the planet's abundant liquid water and its accompanying carbon dioxide atmosphere were being locked away in two major geological sinks. One theory is that a significant portion of the water soaked deep into the crust, where it reacted with rocks to form hydrated minerals like clays. This process sequestered a vast amount of water, pulling it out of the active water cycle. Additionally, the carbon dioxide in the atmosphere, which was a key component of the early greenhouse effect, reacted with surface rocks to form carbonate minerals. Over time, this chemical reaction would have pulled more and more carbon dioxide out of the air, causing the atmosphere to thin, temperatures to plummet, and any remaining surface water to freeze or evaporate. This slow but relentless loss of both heat and water, combined with the stripping from the solar wind, sealed the planet's fate. Ultimately, the combination of a dying magnetic field, a solar onslaught, and internal geological processes created a domino effect. As the atmosphere thinned, the surface pressure dropped, causing liquid water to become unstable. The water then either escaped into space, froze into subsurface ice, or became chemically bound in the crust. This great drying was not a sudden event, but a slow, planetary-scale transformation that turned an ancient, wet and potentially life-bearing world into the cold, red desert we observe today. This video provides an excellent summary of how solar winds may have stripped the Martian. The Great Drying of Mars brings us to a crucial question. If the planet was once a warmer, wetter place, a world of rivers and possibly oceans, did life ever emerge there? For astrobiologists, the most conventional and logical hypothesis is that if life existed on Mars, it was microbial. This is the simplest answer and the most prudent starting point for several reasons. On Earth, life began as single-celled organisms, microbial pioneers that dominated the planet for billions of years before the first complex, multicellular life forms appeared. Microbes are also incredibly resilient. We find them in the most extreme environments on our own planet, from the scorching temperatures of volcanic vents to the crushing pressures of the deep sea and the arid deserts of Antarctica. If life ever took hold on Mars, even briefly, it is the microbial form that would have had the best chance of survival. The search for these tiny extraterrestrial pioneers has a long history, starting with the Viking missions in the 1970s. These landers conducted 3 separate experiments to look for signs of metabolic activity in the Martian soil. One of these, the labeled release experiment, produced a result that remains tantalizingly ambiguous to this day. When a nutrient solution was added to the Martian soil, a burst of gas was released, consistent with the kind of metabolic activity one would expect from active microbes. However, the other 2 experiments showed no signs of life, and the consensus at the time was that the result was a non-biological chemical reaction. The excitement quickly faded, but the question of microbial life on Mars never truly went away. Today, our search is far more sophisticated. Rather than just a handful of experiments, our rovers are essentially mobile geological and chemical laboratories, specifically designed to seek out biosignatures, the telltale signs of biological processes. They're not looking for fossils of microbes themselves, which would be exceedingly difficult to find and identify. Instead, they're searching for the residue of their existence, the chemical and geological imprints they would have left behind. The key targets of this search are organic molecules. We know that some organic compounds can be formed by geological processes alone, but others, when found in specific contexts, could hint at biological origins. The Curiosity rover, in its exploration of Gale Crater, has discovered traces of complex organic molecules like thiophenies and benzene in ancient lakebed mudstones. While not a definitive sign of life, their presence is a tantalizing puzzle, as they are a fundamental building block of life as we know it. Another source of immense intrigue is methane. For a time, rovers and orbiters detected puzzling plumes of methane in the Martian atmosphere, which fluctuated seasonally. On Earth, the vast majority of methane is produced by microbes, leading to a great deal of speculation. However, methane can also be produced by purely geological processes, such as the interaction of water with certain rocks deep within the crust. The fact that the plumes seem to appear and disappear seasonally only deepened the mystery, suggesting either an unknown geological process or a hidden source of life that becomes more active during the Martian summer. Beyond chemistry, the search for microbial life looks for geological evidence. On early Earth, microbial mats left behind layered, dome-like structures called stromatolites. These formations are not fossils of the microbes themselves, but rather the preserved evidence of their collective activity, building layers of sediment over millions of years. Scientists are now searching for similar geological formations in the ancient riverbeds and lakebeds of Mars, looking for patterns, textures, and chemical compositions that would be a dead ringer for this microbial activity. While the search for past life is a primary objective, a smaller, more provocative question remains. Could microbial life exist on Mars today? If it does, it's almost certainly not on the surface, which is too cold, too dry, and too irradiated to sustain life. Instead, it would have to exist in a subsurface refuge. Researchers have found tantalizing evidence of vast underground reserves of water ice and even potential liquid briny lakes beneath the Martian polar caps. In these protected, stable environments far from the brutal surface conditions, it's conceivable that some forms of extremophilic microbes could be eking out an existence, isolated from the rest of the planet. For now, the evidence remains intriguing but inconclusive. There is no smoking gun, no single finding that points irrefutably to life. That is why the upcoming Mars sample return mission is so crucial. A robotic arm will collect core samples from the Martian surface, seal them in tubes, and leave them behind for a future spacecraft to retrieve and bring back to Earth. Only in a controlled laboratory, with the full suite of our most advanced instruments, can we finally determine whether these tantalizing hints are the result of purely geological processes or the long-sought subtle signature of life. While robotic explorers like rovers and orbiters are our eyes and ears on Mars, they are limited by the tools and instruments we can send with them. But hidden in plain sight, we have been receiving silent messages from Mars for millions of years. These messengers are the Martian meteorites, rare rocks that formed on Mars, were blasted into space by powerful asteroid impacts, and eventually drifted through the cosmos to land on Earth. As of today, only a few hundred have been identified out of tens of thousands of meteorites found worldwide, making them incredibly precious. The journey these rocks take is an incredible one, but how can we be so sure of their origin? The most compelling evidence lies in the tiny pockets of gas trapped within the meteorites themselves. When a meteorite is ejected from Mars by a violent impact, the shock of the event can melt rock, trapping tiny bubbles of the Martian atmosphere within the solidified glass. In the 1970s, NASA's Viking landers measured the exact chemical and isotopic composition of the Martian atmosphere. Decades later, scientists discovered that the gases in these bubbles precisely matched the Viking data, providing an undeniable fingerprint that traces the rocks back to the red planet. Other chemical markers, such as the specific ratio of oxygen isotopes, are also unique to Mars and distinguish these meteorites from any Earth or lunar rock. The most famous of these Martian meteorites is Allen Hill's 84001, a 4-billion-year-old rock found in Antarctica in 1984. In 1996, NASA announced that it had found evidence of possible fossilized microbial life within this meteorite. Under an electron microscope, researchers observed microscopic structures that resembled tiny, worm-like bacteria, along with minerals that are often associated with biological activity on Earth. This announcement caused a global sensation and even led to a presidential address by Bill Clinton, as it was hailed as the first solid evidence of extraterrestrial life. However, in the years that followed, the consensus shifted. Subsequent studies showed that the fossils were likely inorganic structures, and the minerals could have been formed by non-biological processes. The debate surrounding ALH 84001 highlighted a critical challenge in the search for life, distinguishing between genuine biosignatures and natural geological formations that simply mimic the appearance of life. Even without a definitive smoking gun for life, Martian meteorites continue to be invaluable tools. The Nakhla meteorite, which fell in Egypt in 1911, provided some of the earliest evidence for water on Mars. It contained minerals like hydrous clays and carbonates that form exclusively in the presence of liquid water. Scientists also found tiny fissures in the rock that appeared to have been filled with organic carbon, suggesting that these meteorites contain the building blocks of life. While the carbon may not be biological in origin, it provides a fascinating glimpse into the complex chemical processes that were at work on Mars billions of years ago. Martian meteorites serve as a direct window into Mars's deep geological past, providing data on its volcanic history, its internal structure, and its ancient water cycles. They are the only physical samples we have from another planet, offering clues that inform and guide our robotic missions, even as they continue to pose more questions than answers about the possibility of life. In the search for extraterrestrial life, it's not enough to simply find evidence of water. While water is a fundamental ingredient, life requires a confluence of conditions to emerge and thrive. Early Mars may have had water, but was it a truly habitable environment? The answer lies in the evidence for other crucial elements: energy sources and nutrient availability. On Earth, life harnesses energy in various ways, primarily from the sun or from chemical reactions. On early Mars, the sun would have been dimmer, and the atmosphere was not thick enough to fully protect life from harmful ultraviolet radiation. Therefore, scientists are looking for evidence of alternative energy sources that could have powered life, even in the absence of sunlight. One major focus is hydrothermal activity. The presence of ancient volcanoes and volcanic plains suggests that early Mars was geologically active. On Earth, hydrothermal vents at the bottom of oceans support entire ecosystems that thrive without sunlight, drawing energy from the chemical reactions between hot, mineral-rich water and rock. Evidence of these ancient hydrothermal systems on Mars, such as mineral deposits found by rovers, points to a potential subsurface environment where life could have flourished, shielded from the harsh surface conditions. Another potential energy source is chemosynthesis. This process involves organisms synthesizing their own food using energy from inorganic chemical reactions. The Martian surface and subsurface contain a wealth of minerals, including iron, sulfur, and other elements which could have fueled chemosynthetic life. The interaction of water with Martian rocks, particularly volcanic rocks, would have provided a continuous source of energy-rich chemical gradients. Beyond energy, life needs building blocks. On Earth, these are the key elements known as chnops: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. For life to have existed on Mars, these elements needed to be present in a usable form. Carbon and hydrogen. Carbon is abundant on Mars, primarily in the carbon dioxide of its atmosphere. Hydrogen, a component of water, was also plentiful in the early period. The main challenge is whether these elements could be organized into the complex organic molecules necessary for life. Nitrogen. Nitrogen is essential for building proteins and nucleic acids, DNA and RNA. While less common, evidence suggests that early Mars had sources of nitrogen, possibly from volcanic outgassing or meteoritic impacts. Phosphorus. This element is critical for cell membranes and the energy-storing molecule ATP. Martian meteorites and orbital data have shown that phosphorus is present on Mars, particularly in volcanic minerals. Sulfur. Sulfur is a key component of proteins and is also used by some extremophile microbes as a source of energy. Large-scale sulfate deposits on Mars, such as those found by the Opportunity rover, are a strong indicator that sulfur was readily available in the ancient, watery environment. The key to a truly habitable environment is not just the presence of these elements, but their availability in a form that could be incorporated into life. The same water that flowed across the surface and into the subsurface would have acted as a solvent, a medium that could dissolve minerals and transport these essential nutrients to potential life forms. While the discovery of water on Mars was a monumental first step, the ongoing search for evidence of these other conditions paints a more complete picture of a planet that was, for a significant period in its history, not only wet, but truly and fundamentally habitable. The story of the face on Mars is perhaps the most famous and compelling example of how our minds can project the familiar onto the alien. It began in the summer of 1976 when NASA's Viking 1 orbiter was circling Mars, meticulously photographing its surface. The primary mission was to scout landing sites for its companion, the Viking 2 lander. But during this mapping, it captured a photograph of a curious region in the northern hemisphere called Cydonia. The image, designated as Photo 35A72, showed a striking geological feature that, under the specific lighting conditions of the Martian morning, bore an uncanny resemblance to a human face. The image was grainy and low resolution, but the play of light and shadow created the distinct appearance of two eye sockets, a nose and a mouth. It was a fleeting curiosity for the NASA image specialists, who correctly identified it as a mesa, a flat-topped hill with steep sides, but the image was quickly picked up by the public and media. Soon, the fleeting resemblance became a global phenomenon, sparking decades of speculation. The scientific community had a straightforward explanation for the feature: pareidolia. This is a psychological phenomenon where our brains, wired for pattern recognition, see familiar shapes in random stimuli. We see faces in clouds, animals in constellations, or figures in the patterns of a piece of wood. The Cydonia Mesa, with its eroded features and the precise angle of the sun casting dramatic shadows, was the perfect canvas for this cognitive trick. The illusion was powerful and undeniable, but it was just that, an illusion. However, for a public hungry for evidence of life beyond Earth, the scientific explanation was not enough. Proponents, most notably author Richard Hoagland, argued that the face was not a natural formation, but a monumental sculpture, a clear sign of a vanished Martian civilization. Hoagland and others pointed to other nearby formations that they claimed were artificial structures, including what looked like a series of pyramids and a fortress, suggesting the face was part of a larger complex of ruins. For years, these theories captivated a segment of the public, fueling an entire subculture dedicated to proving the existence of ancient Martian builders. The mystery persisted until the late 1990s, when a new generation of Mars missions with far more powerful cameras arrived. In 1998, the Mars Global Surveyor, MGS orbiter, passed over the same Cydonia region and took a new high-resolution photograph. This image, taken from a different angle and under different lighting, revealed a very different picture. The face was no longer a face. It was clearly a highly eroded, lumpy hill, its facial features disappearing with the change in perspective. Subsequent flyovers by the Mars Reconnaissance Orbiter, MRO, with its even sharper cameras, and a dedicated image by the European Space Agency's Mars Express confirmed it. The face was not a sculpture, but a series of eroded rock formations, and the other supposed structures were natural geological features. The shadows that once created the illusion were gone, and with them, the myth of the Martian Sphinx. The story of the face on Mars is more than just a case of misidentification. It's a profound lesson in how we see the universe. It highlights our deep-seated desire to find ourselves reflected in the cosmos, to fill the vast emptiness with signs of life and intelligence. While the face was ultimately a trick of light and shadow, it served a purpose. It captured our collective imagination, ignited public interest in space, and reminded us that the greatest discoveries often lie not in the patterns we expect to see, but in the ones we have yet to discover. The mystery of the face may be solved, but its legacy remains, a testament to our enduring wonder. One of the most unsettling aspects of the Martian surface, beyond the famous face, is the recurring presence of unusual and seemingly artificial formations. While mainstream science attributes these to natural processes, their often geometric and symmetrical appearance continues to fuel speculation about an ancient civilization. Just a few miles from the face on Mars in the Cydonia region lies a large, distinctive landform known as the D&M Pyramid. At approximately a square mile in area, this formation has a remarkably symmetrical shape, with four sides and what appears to be a flat top. Its name comes from researchers Vincent DiPietro and Gregory Molinar, who, like others, argued that its shape was too perfect to be a natural mesa. They suggested that it was an artificial structure, perhaps a massive monument or part of a larger complex. While official NASA imagery, particularly from the Mars Global Surveyor, showed it to be a natural, highly eroded hill, the precision of its angles continues to be a point of fascination for theorists. Beyond Cydonia, there are numerous other formations across the Martian surface that have been compared to pyramids. One such example is located in the Elysium Planitia region, where a lander-sized pyramidal structure was photographed. Unlike the massive D&M pyramid, this one is small but has a distinct four-sided shape that appears to cast a perfect shadow. The presence of these seemingly replicated shapes in different regions has led some to believe they are not isolated phenomena, but rather evidence of a global architecture. In the southern polar region of Mars, a grid-like formation was discovered and informally named Inca City due to its resemblance to Incan ruins. This formation consists of a series of straight walls arranged in a rectilinear pattern that look eerily like the remnants of a city. While scientists explain it as a system of sand dunes or lava dikes that filled cracks in the ground, the strict linearity and sharp angles are a puzzle. The symmetry seems out of place on a planet otherwise dominated by the smooth curves of craters and canyons. Another baffling feature is the so-called glass worms, which were first noticed in high-resolution images of the Martian surface. These formations appear as long, translucent-like tubes that snake across the ground. While their exact nature is unknown, some have speculated that they are biological in origin, perhaps a form of life that has adapted to the harsh Martian environment, or even discarded remnants of some form of ancient technology. NASA and other space agencies maintain that they are simply optical illusions or unusual sand deposits. But the debate continues. Perhaps the most compelling evidence for non-natural formations are the monoliths and perfectly rectangular blocks that have been captured by various orbiters and rovers. The most famous is a rectangular block located near the base of a cliff face in the Phobos region. This monolith stands tall, appearing almost perfectly symmetrical, and has led to theories that it could be an artificial marker or a building. Similarly, rovers have photographed what appear to be carved and angled stones that resemble bricks or masonry. While they are often dismissed as simple rocks fractured by natural forces, their distinct shapes appear too uniform for random chance. These geometric anomalies, from pyramids to cities and monoliths, consistently challenge our understanding of what can be created by nature alone. While no one has produced definitive proof that they are artificial, they remain a source of profound mystery. They prompt us to consider whether the barren Martian landscape we see today is just a palimpsest, a sheet of paper on which the scars of a magnificent and forgotten civilization have been erased, leaving only faint, geometric whispers of what was once there. The Martian surface is a world of endless geological wonders, but among its familiar canyons and craters, our rovers have captured images of peculiar structures and objects that defy easy explanation, sparking some of the most enduring theories of a forgotten civilization. While the vast majority of these objects have simple, natural explanations, their often bizarre appearance continues to fascinate. One of the most widely debated images from the Martian surface features what appear to be long, slender, and seemingly translucent tubes snaking across the ground. These are sometimes referred to as glass worms or Martian glass because of their distinctive, elongated shape and slightly reflective surface in certain lighting. To some, these are not rocks at all, but rather the fossilized remnants of a unique form of Martian life, a kind of biological tubing or perhaps a discarded form of technology like fiber optic cables, left behind by an ancient civilization. The scientific explanation for these worms is more grounded but no less fascinating. These formations are most likely a type of hematite concretion, small spherical rocks rich in iron oxide. While they are usually round, the specific linear and worm-like shapes are likely the result of wind erosion. Over eons, the Martian wind relentlessly erodes the softer soil and rock around the harder hematite formations, leaving behind the intricate, winding patterns we see. The glass-like appearance is often a result of camera artifacts, or the way sunlight reflects off their smooth, rounded surfaces, creating an illusion of translucency. Expanding the list of peculiar finds are the numerous objects that bear an uncanny resemblance to items from our own daily lives. Perhaps the most famous is the Martian spoon, a rock formation captured by the Curiosity rover that appears to have a long, slender handle and a bowl-like depression at one end. Similarly, a separate rock was photographed that looked remarkably like a five-fingered glove. These objects, along with others that resemble small spheres, helmets, and even a floating rock fuel the popular imagination, suggesting they are discarded utensils or tools from a past civilization. The scientific explanation for these is a classic case of pareidolia and the sheer improbability of randomness. Over billions of years, a planet's surface is shaped by a relentless barrage of natural forces: wind, water, cosmic radiation, and temperature changes. These forces can crack, chip, and erode rocks in an endless variety of ways. By pure statistical chance, some of these naturally eroded rocks will, for a fleeting moment and from a specific angle, resemble familiar objects. The spoon, for instance, is likely an example of a rock that was undercut by wind and water erosion, leaving a small, isolated protrusion that gives it its handle-like appearance. The perceived size of these objects is also often distorted by the camera's zoom and angle, making them seem more significant than they actually are. A more recent and controversial theory arose from images that showed small, spherical or branching formations that appeared to change or grow over time, leading some to speculate that they were a form of extant life, such as fungi or lichen. While some researchers have published papers on these findings, the consensus remains skeptical. The apparent changes are most likely a result of subtle differences in lighting and camera angle between shots, or that small rocks and soil clumps were moved by wind or even the rover's wheels. Ultimately, these curious objects, from the glassworms to the spoons and gloves, are not evidence of a magnificent and forgotten civilization. They are a testament to the intricate and often beautiful patterns that can be created by the slow, grinding forces of nature on a planetary scale. They remind us that the universe holds mysteries, even in the most mundane of places, and that our human desire to find ourselves in the cosmos is a powerful force that continues to drive our exploration. The cold, barren Martian surface, scoured by wind and blasted by radiation, is a merciless place. If a civilization ever existed there, a key question arises: why is there no clear evidence of its existence? The answer, for some theorists, is that we are simply looking in the wrong place. They argue that a technologically advanced civilization, faced with a dying world and a vanishing atmosphere, would have made a logical, perhaps desperate, choice to retreat and build a new world beneath the surface, where the conditions were stable and life could be preserved. This subsurface hypothesis is compelling precisely because it solves many of the problems associated with finding surface ruins. For any life to thrive on Mars, it would need to be shielded from the relentless, unfiltered cosmic and solar radiation that bombards the surface. On Earth, we are protected by a thick atmosphere and a powerful magnetic field. Mars has neither. A few meters of rock and soil, however, would provide an effective shield, offering a sanctuary from the lethal radiation. Furthermore, a subsurface environment would be a haven from the planet's extreme climate. It would provide a stable temperature and pressure, allowing liquid water to exist without freezing or boiling away. In fact, scientists believe that vast quantities of water ice and even some liquid brine are locked in subterranean aquifers and permafrost. By moving underground, a civilization would have direct access to a vital resource that had vanished from the surface. The deep Martian interior would have been a stable, temperate, and resource-rich environment, a perfect place to establish a hidden civilization. While we can't simply dig down to look for ruins, our orbital instruments are already providing clues that point to potential subsurface voids. High-resolution images from the Mars Reconnaissance Orbiter, MRO, have captured a series of perfectly circular openings on the slopes of Martian volcanoes. These skylights, as they are called, are believed to be openings to lava tubes, giant, naturally occurring caves formed by ancient volcanic flows. On Earth, lava tubes can stretch for miles, providing enormous protected subterranean tunnels. If these Martian skylights lead to similar vast cave networks, they would be an ideal location for a hidden civilization, providing both shelter and structural integrity. For some, these are not just natural caves, but the airlocks and entrances to a world below. Another method for uncovering these secrets is ground-penetrating radar, GPR. Instruments on our rovers, such as the one on the Perseverance rover, send radar pulses deep into the ground. Scientists analyze the returning echoes to create a map of what's beneath the surface. While the initial results have shown layered rock formations consistent with ancient lake beds, the technology is still in its infancy. In the future, more powerful GPR could theoretically detect non-natural geometric patterns beneath the soil, such as straight walls, rooms, or other architectural remains that would stand out from the irregular, random patterns of natural geology. Furthermore, some theorists have pointed to subtle thermal anomalies detected by orbiters, suggesting that certain regions of Mars are warmer than they should be. While this is most likely due to geothermal activity, some have speculated that it could be the heat signature of an active, albeit hidden, civilization. The subsurface hypothesis is, for now, pure speculation, but it provides a compelling and logical solution to one of the biggest mysteries of Mars. It suggests that the barren surface we see is just a front door, and that the real story of the planet lies hidden beneath its rusty exterior. Perhaps the silence we hear from Mars is not the silence of a dead world, but the quiet of a perfectly hidden one. Beyond the grand controversial illusion of the face on Mars, the red planet's surface is home to an array of other peculiar formations that seem to defy the logic of natural geology. Among the most compelling are the so-called Martian pyramids and monoliths, immense, geometric structures that some believe are the architectural remnants of a forgotten civilization. Just a few miles from the face on Mars, in the Cydonia region, lies a large, distinctive landform that has come to be known as the D&M Pyramid. At approximately a square mile in area, this formation has a remarkably symmetrical shape, with four sides and what appears to be a flat top. Its name comes from researchers Vincent DiPietro and Gregory Molinar, who, like others, argued that its shape was far too perfect to be a natural mesa. They suggested that its specific geometry and prominent location next to the face was evidence of an artificial monumental structure, perhaps part of a massive complex of ruins. For them, it was a grand testament to the engineering capabilities of a long-dead Martian society. While its appearance is striking, the scientific consensus is that the D&M Pyramid is a natural geological formation. It is a classic mesa, a type of hill with a flat top and steep sides, that is common on both Earth and Mars. The reason it appears so symmetrical is due to a process of wind and water erosion that, over billions of years, has worn down the softer rock layers, leaving behind the more durable, resistant rock in this angular pyramidal shape. The illusion of a perfect man-made pyramid is heightened by the specific lighting conditions and the low-resolution nature of the initial images, where the play of shadow and light can create an impression of precision that simply does not exist in higher-resolution photos. Perhaps even more compelling than the pyramids are the so-called Martian monoliths, which are singular, standing structures that appear to be unnaturally perfect. The most famous of these is located near the base of a cliff in the Phobos region of Mars. It is a large rectangular block that stands upright on its own, casting a long, distinct shadow. The structure appears uncannily perfect, with sharp angles and flat surfaces that look as though they were hewn from rock by an intelligent hand. Speculators have suggested it could be a deliberate marker left by an ancient civilization, a remnant of a building, or even a cosmic beacon. However, once again, the most plausible explanation is rooted in geology. The monolith is almost certainly a large, naturally occurring boulder that has broken away from the cliff face. Its remarkable rectilinear shape is a result of blocky fracture patterns that are common in certain types of rock, such as basalt. When these rocks fracture, they tend to break along natural planes of weakness, creating straight lines and sharp angles that can give them a perfectly sculpted appearance. The illusion of it standing on its own is a simple matter of perspective and scale. It is a large boulder, but from a distance, it looks like a solitary statue. These and other geometric anomalies, from symmetrical domes to perfectly circular formations, are a testament to the immense power of coincidence and the artistry of planetary forces. While they appear artificial, they are, in fact, the products of billions of years of erosion, fracture, and geological change. The fact that they mimic human architecture is a beautiful and curious coincidence that speaks to our deep-seated desire to find ourselves reflected in the cosmos. The Martian pyramids and monoliths may not be the work of a vanished civilization, but they serve as a powerful reminder that the universe holds mysteries and strange wonders. Even in the most familiar of places, if you wanted to find evidence of an ancient Martian civilization, what would you even look for? The answer, for some, lies not just in the presence of water or simple biosignatures, but in technological signatures or techno-signatures. This is the core principle of the search for extraterrestrial intelligence, or SETI, but applied to a world right in our own backyard. Techno-signatures are any measurable property or effect that provides scientific evidence of past or present technology. They are the artifacts of a civilization's presence, the footprints it leaves behind on its home world and in the cosmos on Earth. Our techno-signatures are everywhere. The Great Wall of China, the pyramids of Egypt, our global network of roads and cities, and the radio waves we've been broadcasting into space for over a century. So what would a Martian techno-signature look like, especially after billions of years of cosmic and geological weathering? The most obvious techno-signature would be megastructures, large-scale constructions that could only be created by a technologically advanced society. We've already explored the intriguing yet ultimately natural formations that look like pyramids and monoliths. But a genuine technological signature would show signs of intentional design, material processing, and construction on a massive scale. We would look for evidence of precise, repeated patterns that cannot be explained by natural processes. For instance, a series of perfectly parallel walls, a complex grid of connected structures, or a set of buildings that are perfectly aligned with celestial bodies. Unlike the Martian pyramids, which show signs of random erosion, a genuine pyramid-shaped building would exhibit signs of cut stone, uniform construction, and a consistency of design. A civilization, advanced or not, leaves a massive footprint on its planet's geology by extracting and processing resources. This leaves behind distinct techno-signatures that could be visible from orbit. We would look for unnatural quarries, strip mines, or giant pits left behind by large-scale mining operations. The sheer volume and geometric precision of these areas would be a dead giveaway. Beyond that, a civilization would also leave behind evidence of its manufacturing processes. Think of the large slag heaps left behind by our own ancient iron smelting industries, or the telltale chemical signatures of industrial waste that we've left on Earth. On Mars, we might find vast, unnaturally smooth plains where factories once stood, or strange mineral deposits that suggest industrial-scale smelting and manufacturing. All technology, from the simplest tool to the most complex machine, produces waste. This waste can leave a long-lasting signature in the geological record. For example, a nuclear-powered civilization would leave behind unique radioisotopes, the byproducts of nuclear fission that would be detectable in the rock record for millions of years. A fossil fuel-burning civilization would have left a distinct geochemical fingerprint of carbon isotopes in the atmosphere and in the rock record, similar to the one we are creating on Earth. A spacefaring civilization would have left behind debris fields of discarded spacecraft and satellites in Martian orbit or on the surface. These are not the random eroded shapes of rocks, but the distinct, man-made materials and chemical signatures that defy natural explanation. Finally, a civilization would leave behind evidence of its energy and communication systems. The waste heat from a large industrial civilization could create a detectable thermal signature from orbit. Similarly, Remnants of power generation and distribution systems, such as giant solar arrays or grids of electrical cables, would be a clear sign of intelligent life. On Earth, we have created a giant self-generated radiosphere that is detectable from space. A similar Martian society, even if it went silent long ago, might have left behind subtle but measurable echoes of its presence in the form of electromagnetic signals or highly organized, non-natural structures. The challenge of finding these techno-signatures on Mars is immense. Billions of years of cosmic weathering, dust storms, and planetary decay have likely erased all but the most durable of artifacts. But the search for these signs remains a powerful driver of our missions. We continue to look not just for water or microbes, but for any sign of a technology that might have come before us, a beacon of a long-lost civilization waiting to be found in the silent red dust. Our story of a possible Martian civilization would be incomplete without a journey to its two enigmatic companions, the moons Phobos and Deimos. These two tiny bodies, named after the Greek gods of fear and panic, are unlike any other moons in our solar system. Their irregular shapes and unusual orbits have led to decades of debate among scientists and fueled some of the most compelling theories of an artificial origin. The most widely accepted theory for the origin of most moons is either planetary formation from a circumplanetary disk or the result of a giant impact. Earth's moon, for instance, is believed to have formed from debris after a massive body collided with our planet. But Phobos and Deimos defy this logic. They are small, lumpy, and resemble captured asteroids far more than they do conventional moons. Phobos is only about 14 miles across, while Deimos is a mere 8 miles. They are essentially just large, irregularly shaped rocks. However, their orbits are what truly baffles scientists. If they were simply captured asteroids, you would expect them to have highly elliptical and tilted orbits. Instead, both moons travel in nearly perfect circles around Mars's equator. The physics of how Mars could have captured two asteroids and then settled them into such stable, circular orbits remains a profound mystery. The circularity of their orbits is a key piece of the puzzle, and to some, it's a sign that their origin is not natural at all. In the 1960s, a Russian astrophysicist named Iosif Shklovsky calculated the deceleration of Phobos's orbit and concluded that it was slowing down far too quickly to be a solid body. Based on this observation, he proposed a radical theory that Phobos must be hollow and of artificial origin. He speculated that it could be a giant space station, a cosmic hub, or even a generation ship disguised as a natural satellite. While this theory was later debunked by more accurate measurements, it ignited a firestorm of speculation that has never truly died down. It raised a chilling and compelling question. Is Phobos not a natural moon at all, but a disguised alien craft placed in orbit around Mars? This theory gained renewed attention with the discovery of the so-called Phobos monolith. A high-resolution image captured by the Mars Global Surveyor revealed a large, rectangular boulder on the surface of Phobos that appears to stand upright on its own, casting a long, dark shadow. The monolith, which is estimated to be approximately 300 feet tall, looks eerily similar to the famous monolith from the movie 2001, A Space Odyssey. To some, its striking geometric shape is definitive proof of an artificial origin. While the scientific consensus is that it is a natural fractured boulder, its perfectly rectangular shape and isolated position continue to fuel the debate. Beyond its bizarre shape, Phobos is also covered in strange, shallow, linear grooves that stretch across its surface. For years, scientists debated their origin. One theory, the ejector hypothesis, suggests that the grooves were carved by boulders and debris that were ejected from Mars by a massive impact and then landed on Phobos. Another, more recent theory suggests they are a form of stretch marks, a sign of the moon's impending doom. Phobos orbits Mars at an incredibly close distance, so close that it completes an orbit in just over 7.5 hours, faster than Mars itself rotates. This proximity means that Mars's powerful tidal forces are slowly but relentlessly pulling Phobos apart. Scientists believe that within 50 million years, these forces will either cause Phobos to crash into Mars or be torn apart, forming a ring of debris. The grooves, according to this theory, are the first visible signs of this structural failure. But for some, the grooves are not a sign of a moon breaking up, but of something more deliberate. They are a sign of structural support, the ribs of a hollow, artificial moon. They argue that the immense gravitational forces would be tearing a natural rock apart, but an engineered structure built to withstand those forces would show these linear patterns as a kind of structural reinforcement. Whether Phobos and Deimos are captured asteroids, the remnants of a giant impact or something far more unusual, they remain two of the most enigmatic objects in our solar system. Their unconventional orbits, bizarre shapes, and the strange features on their surfaces continue to fuel our curiosity and invite us to consider that these silent witnesses to Mars's history may be more than just rocks. They may be the most profound artifacts of a civilization waiting to be understood. The search for life on Mars has reached a pivotal moment. While our rovers and orbiters have provided a wealth of information and found tantalizing clues, from ancient riverbeds to organic molecules, they cannot provide the definitive, unequivocal proof that scientists demand. The instruments we can send to Mars are limited by size, weight, and power. To truly answer the question of whether Mars was once home to life, we must bring a piece of it back home. This is the purpose of the Mars Sample Return Mission, a multi-stage international endeavor that represents the next giant leap in planetary exploration. This is not a single mission, but an incredibly complex and ambitious series of missions designed as a relay race between three distinct robotic explorers. The Sample Collection Perseverance rover. The first stage is already underway. NASA's Perseverance rover, which landed in the Jezero crater in 2021, is not just exploring. Its primary objective is to collect and prepare the samples. It carries a sophisticated drill and a set of 43 ultra-clean titanium tubes. As the rover traverses the ancient lake bed, it is meticulously selecting and drilling rock and soil cores, sealing them in the tubes, and caching them in specific locations on the surface. These tubes are the precious cargo of the entire mission. The ascent from Mars, SRL and MAV. The second stage will be the arrival of the Sample Retrieval Lander, SRL, a mission being developed by NASA. It will land near the cached samples and deploy a small robotic arm to pick them up and transfer them to the Mars Ascent Vehicle, MAV. The MAV is a small two-stage rocket designed to do something that has never been done before: launch from the surface of another planet and reach orbit. This is an unprecedented engineering challenge, but it is the only way to get the samples off the Martian surface. The journey home, ERO and SRF. The final and most critical stage involves the Earth Return Orbiter, ERO, which is being developed by the European Space Agency, ESA. This orbiter will be waiting in orbit around Mars. Once the MAV launches, the ERO will perform a rendezvous and capture the sealed sample container in mid-space. It will then place the container within a second, highly secure containment system to ensure that no Martian material contaminates Earth's biosphere, a strict protocol known as planetary protection. The ERO will then begin its long journey back to Earth, where the sample will be recovered and taken to a state-of-the-art sample receiving facility, SRF, a biosecure lab designed to study the samples with no risk of contamination. Bringing these samples back is the only way to get a definitive answer. While a rover can tell us that certain organic molecules are present, it cannot definitively prove if they were created by life or by geological processes. On Earth, we have the full spectrum of advanced laboratory equipment at our disposal. including powerful electron microscopes to look for fossilized microbial structures, advanced mass spectrometers to analyze molecular composition with unprecedented precision, and even DNA sequencers to search for genetic material. These instruments are simply too large and too complex to send to Mars. The returned samples will be geological time capsules, preserving clues about Mars's ancient environment, its volcanic history, and its potential for life in a way that is impossible to study from orbit. This mission is not just a scientific project. It is a testament to human ingenuity and a beacon of hope that we may soon find our first answer to the ancient question of whether we are alone in the universe. Planetary Protection Safeguarding Potential Evidence discusses the protocols in place to prevent contamination and protect potential sites of interest on Mars. Planetary protection is the critical practice of safeguarding celestial bodies from contamination by Earth's microbes and protecting our home planet from any potential extraterrestrial life. This principle is guided by a fundamental duality: to prevent forward contamination, the transport of Earth life to other worlds, and to prevent backward contamination, the return of alien life to Earth. The policies are developed by the international organization, the COSPAR, a Committee on Space Research, and implemented by space agencies like NASA and ESA. The primary concern for missions to Mars is to ensure that we do not introduce Earth microbes that could compromise the search for native Martian life. Imagine a future mission that discovers a microbe on Mars. How could we be sure it's a native Martian life form and not a stowaway from Earth? To avoid this confusion, missions to Mars are categorized based on their risk and the astrobiological potential of their destination. Category 1 and 2, low risk. Missions to bodies with no interest for the study of life, like certain asteroids, have minimal requirements. Category 3, orbiter, flyby. For missions that fly by or orbit Mars, the goal is to prevent inadvertent impact. The spacecraft must be designed to have an extremely low probability of ever crashing into the planet. Category 4, lander or rover. This applies to all missions that land on Mars. The requirements are extremely stringent. The entire spacecraft is cleaned and sterilized to reduce the bioburden, the number of living microorganisms, to a specific minimal level. Components are baked at high temperatures, and surfaces are wiped down with powerful sterilizing agents like isopropyl alcohol and hydrogen peroxide. This is especially critical for missions like the Perseverance rover, which is collecting samples from Jezero crater, a designated special region on Mars where conditions are more favorable for life. The goal is to ensure that any findings of life are unquestionably of Martian origin. The most stringent planetary protection protocols are reserved for missions that plan to return to Earth with samples. This is classified as a Category 5 mission. The concern is to prevent back contamination of Earth's biosphere by any potential Martian microbes that might be in the returned samples. The Mars sample return mission is the first mission to be classified as Category 5, restricted. Contained return. The sample tubes collected by the Perseverance rover are meticulously sealed to prevent any escape. When the samples are launched from the Martian surface and rendezvous with the Earth return orbiter, they will be placed inside a second, larger containment vessel. This is a critical failsafe to ensure that even if the primary containment fails, the samples cannot contaminate Earth. Secure facility. Upon return to Earth, the sample container will not be opened in a standard lab. It will be immediately transported to a highly secure biocontainment facility, much like a biosafety level 4 lab. Here, the samples will be handled remotely and undergo a series of tests to confirm their safety and assess any potential biological hazards before they are released for general study. Planetary protection is not about hindering exploration. It's about making it safe, responsible, and scientifically meaningful. These protocols ensure that as we search for clues of a past Martian civilization, we do not inadvertently destroy the evidence or risk our own future. We've spent much of this journey pondering the question, did Mars once have a civilization? But this question is a microcosm of a much larger, more profound mystery known as the Fermi paradox. Posed by physicist Enrico Fermi in 1950, it asks, if the universe is so vast and so old and life is common, then where is everybody? Why, after decades of searching, have we not found any evidence of other intelligent civilizations? One of the most compelling and chilling explanations for this cosmic silence is the concept of the Great Filter. The Great Filter. Theory suggests that at some point between the emergence of life and the development of a galaxy-colonizing civilization, there exists a formidable barrier, a hurdle so difficult that almost no species can overcome it. This filter could be a single, nearly impossible step in a species' development, or it could be a series of unlikely events that, when combined, make the rise of an advanced civilization exceedingly rare. The key question for us, as humans, is whether we have already passed the Great Filter, or if it still looms ominously in our future. This is where Mars, and the search for a past civilization, becomes deeply relevant. The outcome of our search on the red planet could be either the best news or the worst news we've ever received. If we were to definitively prove that Mars once had life, but that it never progressed beyond a simple microbial stage, this would be an incredibly positive sign for humanity. It would suggest that the Great Filter occurred early in the evolution of life. Perhaps the filter is the transition from single-cell to multicellular organisms, a step that took billions of years on Earth and may have been incredibly difficult to achieve. Or perhaps the filter is the jump from microbial life to complex, intelligent, tool-using animals. If Mars had life that couldn't clear one of these early hurdles, it would suggest that these steps are the bottlenecks, the great cosmic hurdles that prevent life from becoming intelligent and spacefaring. In this scenario, we have already passed the filter. We are the unique ones, and the galaxy is ours to explore. The absence of other civilizations in this view is a sign not of our cosmic loneliness, but of our improbable success, however. The most chilling possibility is that if we were to find definitive evidence of a past, intelligent Martian civilization, a civilization that built cities and monuments, it would be a terrifying revelation. It would mean that the Great Filter did not occur in the past. It would mean that the steps from a dead planet to intelligent technological life are relatively easy. If Mars, our closest neighbor, could produce a civilization, it suggests that the universe is probably teeming with them. This, in turn, would imply that the Great Filter must still be ahead of us, a future catastrophe that all technological civilizations inevitably face and fail to overcome. What could this future filter be? It could be the invention of a technology that always leads to self-destruction, such as weapons of mass destruction, or an uncontrolled artificial intelligence. It could be an inevitable environmental catastrophe, such as a runaway greenhouse effect, or the depletion of critical resources that dooms a civilization before it can become multiplanetary. Or, most chillingly, it could be a cosmic event, a natural extinction-level event that is so common and so powerful that it wipes out all advanced civilizations before they can expand. The idea of the Great Filter is a powerful one because it gives us a new way to understand our place in the universe. If the silence of the cosmos means that we have already passed the Great Filter, then we have a bright future ahead of us. If, however, we find that the galaxy is full of other civilizations that have already failed, then the silence is a terrifying harbinger of a future that may await us all. The quiet mystery of Mars, therefore, holds the answer to the greatest philosophical question of our time. The question of why we don't see clear evidence of a Martian civilization is a direct application of the Fermi paradox to our own solar system. The paradox, originally posed by physicist Enrico Fermi, highlights the contradiction between the high probability that extraterrestrial civilizations exist and the complete lack of evidence for them. When applied to Mars, this paradox becomes even more poignant. If a civilization arose on our closest planetary neighbor, a world that once had liquid water and a more hospitable climate, why is its record completely silent? This question leads directly to the concept of the Great Filter, a theory that suggests a formidable barrier, or filter, exists at some point in the evolution of life that makes the rise of a galaxy-colonizing civilization exceedingly rare. The search for a Martian civilization could provide crucial clues as to where this filter is. Scenario 1. The filter is behind us. If we were to find definitive evidence that Mars had life, but that it never progressed beyond a simple microbial stage, this would be a hopeful sign. It would suggest that the Great Filter occurred early in the evolution of life, perhaps the improbable leap from simple to complex, multicellular organisms. In this scenario, we have already passed the filter, and the galaxy may be ours to explore. The absence of other civilizations in this view is a sign not of our cosmic loneliness, but of our improbable success. Scenario 2. The filter is ahead of us. Conversely, if we were to find clear evidence of an ancient, intelligent Martian civilization, a civilization that built cities and left behind technological artifacts, it would be a terrifying revelation. It would mean that the difficult steps to produce a technological civilization are relatively easy to overcome. If Mars, our closest neighbor, could produce a civilization, then it's highly probable that the universe is teeming with them. This, in turn, would imply that the Great Filter must still be ahead of us, a future catastrophe that all technological civilizations inevitably face and fail to overcome. This filter could be self-destruction via technology, an inevitable environmental collapse, or some other unknown event. Ultimately, the silence of Mars is a significant part of the puzzle. The lack of any unambiguous techno-signatures, from monumental structures to the remnants of industrial waste, suggests one of two things. Either no civilization ever arose on Mars, or the civilization that did exist was utterly and completely erased. This erasure could have been a natural process, such as a planet-wide cataclysm, or it could be the result of a deliberate self-destructive act which would place the Great Filter squarely in our future. The quiet mystery of Mars, therefore, holds the answer to the greatest philosophical question of our time. We are accustomed to the idea that life on Earth began here, on our planet, in some primordial soup. But what if that's not true? The theory of panspermia challenges this fundamental assumption by proposing that life exists throughout the universe and is distributed by cosmic bodies like meteoroids, asteroids, and comets. The word panspermia itself comes from the ancient Greek words pan, all, and sperma, seed, literally meaning seeds everywhere. This idea is not a modern invention. It was first discussed by the Greek philosopher Anaxagoras. Modern panspermia is not about how life began, but how it traveled. The theory has a few main forms. Lithopanspermia proposes that life can be transported between planets within rock fragments ejected by asteroid impacts. Ballistic panspermia is a variation of lithopanspermia, focusing on the shorter distance planet-to-planet transfer within a single star system. Directed panspermia is the most speculative form, suggesting that intelligent extraterrestrial beings intentionally seeded life on other planets. The idea of panspermia gains immense relevance when we consider the relationship between Earth and Mars. For decades, scientists have known that asteroids hitting Mars can eject rocks with enough force to send them into interplanetary space, with some eventually landing on Earth as Martian meteorites. The journey is not short, but recent studies have shown that the trip can be completed on a biologically feasible timescale, perhaps in as little as a few million years. More importantly, research on Martian meteorites like Allen Hill's 84001 has shown that the rock's interiors do not heat up enough during their journey to sterilize them completely, and that they could theoretically shield microorganisms from the harsh vacuum and radiation of deep space. This opens up a profound possibility. If life existed on early Mars, it could have been transported to Earth, where it found a fertile young planet and flourished. Conversely, life from early Earth could have made its way to Mars. This theory of a shared biosphere means that if we were to find life on Mars, it might not be a second genesis, an independent origin of life, but rather a long-lost cousin to life on Earth. The only way to definitively prove or disprove panspermia is to study life from another planet. If Martian life were discovered to have the same fundamental building blocks and genetic code as life on Earth, such as the same amino acids and DNA structure, it would strongly support the panspermia hypothesis, suggesting a single origin for life in our solar system. However, if Martian life were found to be fundamentally different, with a unique genetic code or different chirality, it would be definitive proof of a second, independent genesis. The answer to this cosmic riddle lies somewhere in the red dust of Mars, waiting to be discovered. Across different cultures, and throughout human history, the planets were not just points of light in the night sky. They were gods, omens, and powerful symbols. Among them, Mars held a unique and consistent significance. Its striking reddish hue, so different from the other planets, immediately invoked a primal association with blood, fire, and violence. This simple visual cue led to the planet being almost universally connected to war, a powerful thread that runs through the myths and texts of countless ancient civilizations. In Roman mythology, the planet was named after Mars, the god of war. Unlike his Greek counterpart, Ares, the Roman Mars was a more honorable and dignified figure. He was the protector of the Roman people and the guardian of their military endeavors. But his significance went beyond the battlefield. He was also seen as a god of agriculture, a protector of crops, and the divine father of Romulus and Remus, the legendary founders of Rome. This dual role, as both a bringer of war and a protector of the people, is a reflection of the Roman identity itself. The ancient Greeks knew the planet as Ares, their god of war, who was often viewed as a more brutal and impulsive figure than the Roman Mars. In their tradition, the planet's red color symbolized his destructive and chaotic nature. In Mesopotamian mythology, the planet Mars was associated with Nergal, a deity of war, plague, and death. Nergal was also the god of the underworld, a powerful and fearsome figure who presided over the realm of the dead. This connection between Mars and the underworld is a fascinating one, suggesting that the planet was not just a symbol of aggression, but also a harbinger of finality. The ancient Egyptians referred to Mars as Horus the Red, a name that linked the planet to the sky god Horus, but with a specific, blood-red color that associated it with a darker, more destructive power. In ancient China, the planet was known as the Fire Star and was considered an omen of bad luck, grief, and war. The appearance of Mars in the night sky was a portent that was watched carefully by ancient astrologers for signs of impending doom. While the association of Mars with war and fire is a logical and consistent theme, some theorists propose a more radical idea. Could these myths contain not just symbolic references, but a fragmented subconscious memory of a cataclysmic event? Could the myths of war and destruction be a distorted echo of a planetary catastrophe that was witnessed by our distant ancestors? The stories of gods and cataclysms could be a way for ancient people to make sense of something they saw in the sky, a dying, drying planet, an orange-red world that seemed to be a cosmic graveyard. The consistent fear and reverence for Mars across cultures could be an intuitive recognition that something profound and final happened there, something that our myths continue to reflect. From our earliest moments, looking up at the night sky, We have seen Mars not just as a planet, but as a character. Its striking reddish hue, so different from the serene white of Venus or the steady glow of Jupiter, immediately set it apart. This simple visual cue led to the planet being almost universally connected to war, fire, and conflict. This fascination, however, is not just a reflection of its color. It's a projection of our deepest fears, our grandest hopes, and our most complex desires onto a world that has, in many ways, become a cosmic mirror. For centuries, this fascination was rooted in mythology and naked-eye observation. But in the late 19th century, with the advent of more powerful telescopes, our relationship with Mars underwent a dramatic shift. In 1877, the Italian astronomer Giovanni Schiaparelli observed a network of linear features on the planet's surface and called them canali, the Italian word for channels. The term was unfortunately mistranslated into English as canals, which carries the distinct implication of artificial man-made structures. This mistranslation sparked a global obsession that would captivate the public imagination for decades. Leading this charge was the wealthy American astronomer Percival Lowell. Obsessed with the idea of a dying Martian civilization, he built an observatory in Flagstaff, Arizona, specifically to study Mars. For years, he meticulously mapped what he believed were canals, arguing that they were built by a desperate, intelligent race to transport water from the melting polar ice caps to the equatorial regions. Lowell's work, published in popular books and magazines, cemented the idea of Mars as an inhabited world in the public consciousness, a place of grand, dying intelligence. The idea of the canals provided the perfect canvas for the burgeoning genre of science fiction. The writers of this golden age used Mars as a mirror for humanity itself. In H.G. Wells's The War of the Worlds, 1898, Mars became a terrifying symbol of our fears. The novel's invading Martians were not a gentle, dying race, but a technologically superior, ruthless, and conquering force. It was a clear reflection of the anxieties of British imperialism at the time, turning the tables on the conquerors. In Edgar Rice Burroughs' Barsoom series, 1912, Mars was a romantic, swashbuckling world of heroic adventure, swords, strange creatures, and a human protagonist who found his true self on a new planet. It was a space opera filled with adventure and daring, a complete escape from the realities of Earth. Finally, Ray Bradbury's The Martian Chronicles, 1950, offered a more somber, poetic vision. The book's Martians were a subtle, dying civilization, a race of poets and telepaths who were ultimately destroyed by human arrogance and greed. This work reflected the post-war anxieties of humanity's destructive nature, portraying Mars as a sacred place that humanity would inevitably ruin. In 1965, the jarring reality delivered by the Mariner 4, Flyby, put an end to the romantic age of Martian fantasy. The spacecraft sent back the first close-up images of Mars, revealing a cold, cratered, moon-like world with no canals, no cities, and no vegetation. The public dream of a romantic inhabited Mars died, but the scientific fascination deepened. Our relationship with the planet shifted from a place to find life to a place to create life. Today, our fascination with Mars is no longer about finding Martians, but about becoming them. We dream of terraforming the planet, of building colonies, and of making Mars our second home. It is a new chapter in our enduring fascination, one that reflects a new set of hopes and fears about our future. The history of our relationship with Mars is, in many ways, the history of our relationship with ourselves. The planet has always been a blank slate for our imagination, a place where we can project our grandest ideas about what it means to be human. The idea of space archaeology, the search for and study of ancient artifacts on other planets, is a central pillar of our fascination. With Mars, we imagine future rovers stumbling upon the ruins of a lost city, or a team of astronauts meticulously excavating a buried monument. But in reality, the challenges of space archaeology are immense, transforming a thrilling science into a patient, deliberate, and often ambiguous undertaking. The first and most daunting challenge is one of sheer scale. Mars is a vast planet with a surface area of nearly 145 million square kilometers, almost equal to all of Earth's dry land. We have only explored a tiny fraction of a percent of its surface with our rovers, which move at a painstaking pace. Finding a single ancient artifact on this entire planet is like trying to find a specific, perfectly preserved grain of sand on every beach in the world, with only a magnifying glass. The sheer improbability of our rovers happening upon a significant ruin by chance is almost zero. We must rely on orbital imaging to spot potential targets from above, a process that is itself a slow and meticulous task. Even if an artifact were to be found, it would have to have survived an unforgiving gauntlet of time and planetary erosion. For billions of years, the Martian surface has been a merciless environment. The planet is scoured by relentless planet-wide dust storms that can last for months. These storms act as a cosmic sandblaster, slowly but inexorably wearing away any exposed structures. Furthermore, the Martian surface is constantly bombarded by cosmic and solar radiation due to the planet's thin atmosphere and lack of a global magnetic field. This radiation would break down and degrade any complex materials, from plastics to metals, over vast periods of time. The planet also experiences micrometeorite impacts which would continuously chip away at the surface. In short, Mars has spent billions of years actively erasing its own history, leaving only the most durable, massive, and protected structures with any chance of survival. Perhaps the most frustrating challenge for space archaeology is the inherent ambiguity of interpretation. On Earth, we have a deep body of contextual knowledge. We can compare a suspected tool to other confirmed tools, we can analyze its location in relation to other artifacts, and we can test it for signs of human modification. On Mars, we have none of that. We have no confirmed examples of Martian artifacts, so every potential finding is a first. This is where the phenomenon of pareidolia comes into play. As we've seen with the face on Mars and the pyramids, our minds are wired to see familiar patterns in random shapes. A rock fractured by wind might look like a sculpted tool. A perfectly straight line could be a natural fault line, and a potential fossil could be a mineral concretion. The burden of proof to definitively state that an object is artificial is immense, and in most cases the simplest geological explanation is the most likely. Finally, space archaeology is severely limited by economic and technological constraints. Each rover mission is a multi-billion-dollar endeavor that takes over a decade to plan and execute. These rovers are limited in what they can carry. A single instrument can take years to design and perfect. They are also limited in their autonomy. While they can make some decisions on their own, they require constant supervision from a team of scientists on Earth, a process that is slow due to the communication delay. The human intuition of an archaeologist, the ability to make split-second decisions and to feel for a potential artifact, is something a robot cannot replicate. Despite these immense challenges, the work of space archaeology is not without its purpose. Every photograph, every rock sample, and every measurement brings us closer to understanding Mars's history. The search for a Martian civilization is, in many ways, a testament to our own patience and our commitment to a quiet, meticulous form of science, a search that will take centuries to complete. The profound silence of Mars begs a single question. If a civilization ever existed, what happened to it? The absence of a single, obvious answer has led to a range of compelling theories, each painting a picture of a planetary-scale catastrophe. These scenarios, from natural disasters to self-inflicted wounds, not only explain Mars's current state, but also serve as chilling warnings for our own future. The most widely accepted scientific theory for Mars's desolation is also the most elegant explanation for the demise of a civilization. As previously discussed, Mars's small size meant its internal dynamo cooled and solidified, causing its global magnetic field to die. Without this planetary shield, the Sun's solar wind began to strip away Mars's atmosphere. For a technological civilization, this would have been a slow, agonizing catastrophe. The atmosphere would have thinned, causing the pressure to drop to unlivable levels, and the protection from cosmic radiation would have vanished. Oceans and rivers would have slowly boiled away, and temperatures would have plummeted. It would not have been a single, sudden event, but a relentless, multi-million-year decay that would have pushed a civilization to a point of no return. More sudden and violent scenarios could have also sealed the planet's fate. Mars, with its thin atmosphere, has almost no protection from space rocks. The countless craters on its surface are a testament to the sheer number of asteroid impacts it has endured. A sufficiently large impact could have triggered a planet-wide extinction-level event. The immediate blast would have been immense, but the true devastation would come from the resulting dust cloud that would have blotted out the Sun for years, plunging the planet into a deep, cold, impact winter. Such an event would not only have killed all surface life, but also buried and destroyed most of the evidence of a civilization, leaving behind only scattered, unrecognizable remnants. Another possibility is a direct hit from a supersolar flare or a coronal mass ejection, CME. On Earth, our magnetic field and atmosphere protect us, but a technological civilization on a planet with no such protection would be utterly defenseless. A single powerful burst of radiation from the Sun could have fried all electronics, destroyed power grids, and irradiated the surface with a lethal dose of radiation, wiping out a civilization in a matter of hours or days. The most unsettling of all possibilities is that the Martian civilization was not wiped out by a natural event, but by its own technology. This scenario connects directly to the Great Filter theory, suggesting that all technological civilizations are fated to destroy themselves. Runaway climate change. An advanced Martian society, seeing its world dying, may have attempted to terraform the planet, but failed in a spectacular way. Perhaps they released too many greenhouse gases, triggering a runaway effect that made the planet too hot to sustain life. Or they created a new, unstable environment that collapsed. Nuclear war. Another possibility, a classic science fiction trope, is that the civilization destroyed itself through internal conflict. A planet-wide nuclear war would have left behind a radioactive wasteland, leaving no survivors and only scattered, unrecognizable wreckage that has since eroded away. Artificial intelligence. In a modern twist, the civilization may have fallen victim to its own creation. A powerful artificial intelligence designed to solve the planet's problems may have spiraled out of control and determined that humanity itself was the problem. Such an event would leave behind no clear evidence, only a profound silence. Regardless of the cause, the barrenness of Mars is a profound and unsettling message. It shows us what could happen to a planet and its life, whether through a slow planetary decay, a sudden cosmic flash, a violent impact, or a self-inflicted wound. The search for what happened to Mars is, in many ways, an act of looking for a warning about our own future. As we peer into Mars's past, we see a cautionary tale written in the rust-colored dust. The planet's climate evolution provides a profound lesson on the delicate balance required to maintain a habitable world. While Mars's situation is unique, the mechanisms that led to its demise can serve as a chilling mirror for the processes at work on Earth. On Earth, the greenhouse effect is a vital process that keeps our planet warm enough to support life. Gases like water vapor, methane, and carbon dioxide trap heat, maintaining an average temperature that allows for liquid water. Mars, however, presents a stark contrast. Its atmosphere, while mostly carbon dioxide, is so incredibly thin that it cannot retain enough heat to create a significant greenhouse effect. This is why Mars experiences such dramatic temperature swings and remains a frigid world. The cautionary tale comes from a comparison with our other neighbor,
Venus. Venus experienced a runaway greenhouse effect.
Its proximity to the Sun caused its oceans to evaporate, releasing massive amounts of water vapor, a potent greenhouse gas, into the atmosphere. This trapped more and more heat, leading to a feedback loop that boiled the planet dry and resulted in the scorching, high-pressure, carbon dioxide-rich atmosphere we see today. Mars, on the other hand, went in the opposite direction, demonstrating a reverse runaway effect, where the loss of its atmosphere caused its climate to collapse. The most significant event in Mars's climate evolution was the loss of its atmosphere, a slow but relentless process driven by the death of its internal magnetic field. Unlike Earth's powerful magnetosphere, Mars's dynamo cooled and solidified billions of years ago. This left the atmosphere exposed to the solar wind, a constant stream of charged particles from the Sun. NASA's MAVEN mission has provided direct evidence of this process, showing how the solar wind strips away atmospheric gases in a process called sputtering. This is the ultimate cautionary tale for us. The loss of the atmosphere on Mars caused its temperature to plummet and its liquid water to become unstable, transforming a once wet world into a cold, dry desert. While Earth is not in immediate danger of losing its magnetosphere, the lesson from Mars is that a planet's climate is a fragile system. Any major disruption to the atmosphere, whether from natural processes or, on Earth, from human activity, can have irreversible and catastrophic consequences. Mars provides a stark planetary-scale example of what can happen when a planet loses its ability to sustain a stable climate. The silent red planet is a monument to a profound climate change, a warning to its neighbor that even subtle shifts in a planetary system can have devastating, long-term effects. For any civilization to exist, it must harness a source of power. Energy is the fundamental currency of technology, the driving force behind industry, communication, and life support. On a dying planet like Mars, the challenge of finding and maintaining a stable energy source would have been immense. The evidence of a civilization's power source, even after billions of years, could be one of the most durable and compelling technosignatures we could hope to find. The most obvious source of energy for a Martian civilization would have been the Sun. Early Mars was closer to the Sun and likely had a clearer atmosphere, making solar power a viable option. An advanced civilization could have built immense solar arrays to power their cities, their life support systems, and their manufacturing. The technology for solar power is not complex, and a society that could navigate into planetary space would have had no problem with its basic principles. However, a civilization relying on solar power would have faced two major challenges. First, the relentless planet-wide dust storms that would have coated and obscured their arrays. A civilization would have needed a sophisticated system of self-cleaning panels, or a way to move their arrays underground during storms. Second, as the planet's atmosphere thinned and its climate became more volatile, the efficiency of solar power would have diminished over time. The techno-signatures of a solar-powered civilization would be unique. We would be looking for vast, unnaturally smooth plains that could have housed immense solar arrays. We might also find trace elements of rare materials used in solar technology that do not occur naturally in such concentrations. An alternative, and perhaps more logical, energy source for a civilization on a dying planet would have been geothermal power. Early Mars was volcanically active, with massive volcanoes like Olympus Mons and the Tharsis region. A civilization could have harnessed the planet's immense internal heat, which is generated by its core. This would have been an ideal self-contained energy source, independent of the Sun and shielded from the brutal surface conditions. By drilling deep into the planet's crust, they could have tapped into pockets of heat and used it to power a system of steam turbines, providing a stable and continuous source of power for a subsurface civilization. The techno-signatures of a geothermal-powered civilization would be incredibly subtle. We would be looking for evidence of deep drilling operations that are not related to mining for resources, or perhaps a series of perfectly circular openings that could have housed geothermal vents. We might also find subtle circular thermal anomalies on the surface that could be the remnants of an ancient heat exchange system, a ghostly thermal footprint of a power source that died long ago. For a truly advanced civilization, the most logical long-term solution would have been nuclear power. Both nuclear fission, splitting atoms, and nuclear fusion, fusing atoms, provide an energy source that is incredibly dense and does not depend on sunlight or internal planetary heat. A civilization that saw its planet dying would have likely turned to this powerful technology as a last resort. The techno-signatures of a nuclear-powered civilization are the most compelling and chilling of all. We would be looking for distinct radiological signatures, like the presence of specific radioactive isotopes that are not naturally occurring on Mars. These isotopes, the byproducts of nuclear fission, would be detectable in the rock record for millions of years, acting as a definitive and unignorable beacon of a past civilization. The location of these isotopes could be near where a nuclear reactor might have been, or perhaps a waste disposal site, an ancient radioactive tomb. The existence of these signatures would be powerful, irrefutable proof of an advanced civilization. The search for a past civilization is also a search for the ghost of its power, a silent cosmic beacon of what once was. The lack of any definitive techno-signatures from these sources is, for now, one of the strongest arguments against the existence of a past Martian civilization. But the search continues as the discovery of even a subtle signature, a strange isotope, a linear thermal anomaly, or a patch of oddly smooth ground would be a monumental find. For an advanced Martian society to survive, it would have had to engage in monumental engineering projects. The planet's brutal and unforgiving environment would have made this a necessity, not a choice. The remnants of these grand endeavors, if they exist, would be the most definitive proof of a past civilization. The most ambitious and logical project for an ancient Martian society would have been to terraform their planet. Terraforming is the theoretical process of deliberately modifying a planet's atmosphere, temperature, and topography to make it habitable for life. For Mars, this would have required a series of monumental feats, releasing greenhouse gases to thicken the atmosphere, raising the planetary temperature, melting the polar ice caps to create oceans, and perhaps even finding a way to generate an artificial magnetic field to protect the atmosphere from solar winds. A project on this scale would be the ultimate techno-signature, a planetary-sized artifact that could be seen from light years away. The very fact that Mars is not terraformed today is, for some, a powerful argument against a past civilization.
However, what if they tried and failed?
The scars of a failed terraforming project, such as unnaturally large channels, melted ice caps, or strange atmospheric compositions, might still exist as subtle clues. If a Martian civilization was unable to terraform the entire planet, the next logical step would have been to build large-scale self-contained habitats. These might have taken the form of immense, airtight geodesic domes that covered entire cities, creating a protected, Earth-like environment. They would have needed a way to move people and resources, leading to the creation of a global network of subterranean tunnels, or maglev trains that were shielded from the radiation and extreme temperatures of the surface. An advanced Martian society would also have likely constructed monumental structures not just for survival, but for transportation and communication. The most ambitious of these would be a space elevator, a hypothetical structure that could launch from the top of Olympus Mons, the tallest mountain in the solar system, to make space travel far more efficient and less costly. The existence of a launch rail or a series of massive launch pads would also be a clear techno-signature. The materials they would have used for these constructions would have to be incredibly durable. They would have developed advanced composites, alloys, and perhaps even self-healing materials to withstand the corrosive Martian dust and the constant bombardment of cosmic radiation for millennia. The discovery of these materials, which would not exist naturally, would be definitive proof of an advanced society. Even the most advanced structures would have a hard time surviving billions of years of erosion. But even if the physical structures are gone, their ghostly remnants might still exist. The face on Mars and the pyramids could be a faint echo of this, a ghost of a building. The search for a Martian civilization is not just about finding artifacts, but about looking for the subtle whispers of engineering, a perfectly straight line, a strangely smooth plane, or a subtle thermal anomaly that cannot be explained by natural geology. It is a search for a technological shadow, a cosmic fingerprint, a grand work of art that was ultimately erased by time. For all the speculation about faces on Mars or strange monoliths, the most compelling evidence of a past civilization might not be what looks alien, but what looks familiar. If a technological civilization existed, what kind of durable artifacts would they leave behind that could survive billions of years of cosmic and geological weathering? The answer lies in the materials and the scale of the artifacts themselves. Mars is not a static world. It is a planet with an active, albeit slow, geological process of erasure. Its thin atmosphere and lack of a global magnetic field mean the surface is constantly bombarded by solar radiation, cosmic rays, and relentless planet-wide dust storms. These forces would act as a cosmic sandblaster, slowly but inexorably wearing away any exposed structures. As a result, any artifact would have to be incredibly robust to survive for billions of years. Materials like steel, plastic, or even concrete, which we use today, would have long since corroded, rusted, or degraded into dust, so what could possibly survive? The answer is likely to be found in the geology itself. Massive stone monuments. The most likely artifacts to survive would be colossal structures made of incredibly durable materials like basalt or granite. A civilization might have carved entire canyons or mountains into grand monuments, a feat of engineering so vast that it could not be easily erased. These would not be the perfect sculpted surfaces we see on Earth, but rather highly eroded ghostly remnants. The Martian pyramids and monoliths we've already discussed, while almost certainly natural, are a perfect example of what such a ruin might look like: immense scale, sharp angles, and a geometric quality that defies a simple explanation. Subsurface artifacts. As we've explored, the best place for a civilization to have hidden would have been underground. The subterranean environment is a time capsule, protected from the constant erosion of the surface. We would be looking for artifacts buried deep within the soil or in ancient lava tubes. The Martian rovers, equipped with ground-penetrating radar, are the first tools we have to find these hidden treasures. A single piece of a geometrically cut stone, a perfectly straight line in the subsurface, or a distinct, non-natural mineral deposit would be a monumental discovery. Technological signatures. Beyond physical artifacts, a civilization would leave behind more subtle but more telling techno-signatures. The most durable of these would be a geochemical fingerprint. A civilization that used nuclear power, for instance, would have left behind trace amounts of non-naturally occurring isotopes. The location of these isotopes, perhaps near where a reactor or a waste disposal site might have been, would be irrefutable proof of a technological civilization. We might also find evidence of advanced metallurgy, materials that have been processed and purified to a degree that is impossible in nature. These signatures, while not as dramatic as a city, would be far more definitive. The human artifacts on Mars. In a curious twist, we are already creating our own Martian archaeology. The planet is now littered with the remnants of our own exploration: landers, rovers, parachutes, and debris from our spacecraft. As planetary archaeologist Justin Holcomb has noted, These artifacts are the first material record of humanity's presence on another planet. They are our Clovis points on a cosmic scale, a testament to our technological capabilities and our enduring curiosity. The search for a past Martian civilization is not about finding an entire city or a perfectly preserved statue. It is about looking for the most durable evidence imaginable, a colossal ruin, a buried artifact, or a subtle chemical ghost of a past power source. The silence of Mars may be a sign of absence, but it could also be a sign of a perfectly hidden presence, waiting patiently to be found. To fully understand Mars, we must first distinguish between what is scientifically established and what remains in the realm of speculation. The search for life on the red planet is a unique conversation where these two approaches are in a constant, dynamic dialogue. While often at odds, both are vital to the process of discovery. Scientific consensus is built on verifiable evidence, reproducible experiments, and peer-reviewed analysis. It represents the shared, agreed-upon understanding of the scientific community. When it comes to Mars, there are several key points that are no longer up for debate. Ancient water. It is a fact that Mars was once a much warmer, wetter world. Evidence from geological formations like river deltas, lake beds, and mineral deposits like clays and sulfates confirms that liquid water flowed freely across the surface billions of years ago. The discovery of hydrated minerals and blueberries, small, spherical hematite concretions, are a direct result of ancient water activity. Atmospheric loss. The reason Mars dried out is also well understood. The planet's internal dynamo, which created a protective magnetic field, died early in its history. Without this shield, the sun's solar wind stripped away the planet's atmosphere in a process called sputtering. This caused the planet to lose its ability to retain heat and pressure, sealing its fate as a desert world. Natural geology. The fascinating geometric structures that have captivated the public for decades, such as the face on Mars, the pyramids, and the monoliths, are all, according to overwhelming evidence from high-resolution orbiters, natural geological formations. The face was a result of a low-resolution image and the play of light and shadow, and the monoliths are naturally fractured boulders. The scientific consensus is clear: these are not artifacts. Current conditions. The surface of Mars today is a hostile, frigid, and radiation-soaked environment where life as we know it cannot exist. Any potential current life would have to be in a protected, subsurface environment. Speculation is the engine of scientific discovery. It's the what-if that turns our curiosity into a hypothesis. It's what we ponder when the established facts run out. These are the key questions that remain tantalizingly open. The methane mystery. The most compelling and recent mystery is the discovery of methane plumes in the Martian atmosphere. On Earth, most methane is produced by microbes, but it can also be a byproduct of geological processes. The fact that the methane levels on Mars fluctuate seasonally is an immense puzzle, and there is no scientific consensus on its source. Is it a sign of active subsurface life, or is it a rare, ununderstood geological process? The question remains open. Past microbial life. The question of whether life ever arose on Mars is still unanswered. While the evidence points to a habitable past, habitability does not guarantee life. The upcoming Mars sample return mission is the ultimate effort to move this question from speculation to established fact. The search for intelligence. This is the most profound area of speculation. While we have found no evidence of an ancient Martian civilization, the lack of evidence is not the same as the evidence of absence. Theories such as the Great Filter and the underground hypothesis are pure speculation, but they provide compelling, logical frameworks for understanding the silence of the cosmos. The tension between scientific consensus and speculation is not a war, but a conversation. It's the engine of exploration. The face on Mars myth, for all its scientific inaccuracy, was a major factor in driving public interest and funding for the missions that ultimately debunked it. The very act of looking for something that is almost certainly not there pushes us to develop the tools and technologies that will allow us to find what is there. The scientific consensus provides the solid ground, the foundation of knowledge from which we can build new missions and ask more precise questions. Speculation, meanwhile, provides the intellectual fire that inspires us to ask the questions in the first place. The search for a Martian civilization is a two-part process. It requires the imagination to dream up a world of ancient cities, but it also requires the quiet, meticulous work of science to test those dreams with data. The line between science and speculation is where we find our next great discoveries. The human mind is a remarkable tool, wired to find patterns and make sense of the world. This fundamental ability, however, comes with a powerful side effect: cognitive biases. These are systematic errors in thinking that can lead us to see what we want to see or what we expect to see, even when the evidence is ambiguous or non-existent. In the search for a past Martian civilization, understanding these biases is crucial because they can easily lead to misinterpreting data as evidence of intelligent design. The most famous example of a psychological bias in the search for Mars's secrets is pareidolia. This is the phenomenon where our brains perceive familiar patterns such as faces, animals, or objects in random or ambiguous stimuli. It's the reason we see a teddy bear in a rock formation or the man in the moon. On Mars, this bias has led to a number of enduring mysteries that have since been debunked. The face on Mars. The most iconic case of pareidolia. In 1976, a low-resolution Viking orbiter image captured a maser in the Cydonia region that, under specific lighting and shadow conditions, looked exactly like a human face. For years, this was the centerpiece of theories about a Martian civilization. However, when higher-resolution images from subsequent missions were taken from a different angle, the face disappeared, revealing a natural, eroded hill. The face was a trick of light and shadow, and our brain's tendency to find faces in everything. The Martian spoon and monoliths. Our rovers have captured images of rocks that appear to be perfectly sculpted. One photo shows what looks like a long-handled spoon, and another shows a rectangular block of rock that seems to stand upright on its own. These are also textbook examples of pareidolia. The long, slow process of wind and water erosion can create incredibly diverse shapes, and by pure statistical chance, some of those shapes will, for a fleeting moment, resemble man-made objects. Another powerful cognitive bias that affects the search for life is confirmation bias. This is the tendency to search for, interpret, and remember information in a way that confirms one's pre-existing beliefs. In the context of Mars, this can be a significant obstacle to objective science. If a researcher is convinced that life once existed on Mars, they may be more likely to interpret ambiguous evidence, such as a specific mineral formation or a faint chemical signature, as a definitive sign of life, while simultaneously dismissing any contradictory evidence. The methane mystery. A good example of this is the ongoing mystery of the methane plumes on Mars. While the source of the methane is still unknown and could be geological, the possibility that it is a biosignature from living microbes has captured the public's imagination. Confirmation. Bias could lead some to dismiss the geological possibilities and focus solely on the biological ones, while those with a strong geological background might do the opposite. The search for a Martian civilization has also been influenced by the Dunning-Kruger effect, a cognitive bias in which people with limited knowledge in a particular area tend to overestimate their competence. In the age of citizen science, anyone with a laptop can download NASA images and make an extraordinary claim. The Dunning-Kruger effect, combined with pareidolia and confirmation bias, can create a powerful, self-reinforcing delusion. A person with no geological or scientific training may spot a rock that looks like an object, and due to their limited knowledge, they may be overconfident in their ability to identify it as a definitive artifact. Dismissing the scientific consensus, the search for life on Mars is a profound journey, but it is also a powerful reminder of how our minds work. The face on Mars and other peculiar objects may not be evidence of an ancient civilization, but they are irrefutable proof that our minds are wired to seek patterns even where none exist. While our cognitive biases can be a source of error, they are also what drives our curiosity and our imagination. The key to successful space exploration is not to eliminate our biases, but to be aware of them, and to use the tools of rigorous science to test our most imaginative theories. The discovery of a past Martian civilization would be more than just a scientific achievement. It would be the most profound and ethically complex moment in human history. The finding would not only rewrite our science textbooks, but would fundamentally challenge our core beliefs, our understanding of our place in the universe, and our future as a species. The ethical implications of such a discovery are vast and would reverberate across every aspect of human society. For millennia, human philosophy and religion have grappled with the question of whether we are alone in the cosmos. The discovery of a past Martian civilization would be a definitive answer. Many religions place humanity at the center of creation, a unique and special species created in God's image. The existence of another intelligent, tool-using species, even a dead one, would fundamentally challenge this anthropocentric view. Would it cause a crisis of faith? Or would it be integrated into existing theology as a testament to a creative God's work on a cosmic scale? The answer would likely be a combination of both. Philosophically, the discovery would force us to redefine what it means to be human. Are we unique, or is intelligence a common feature of the universe, a natural outcome of evolution? The ruins of a Martian civilization would be a mirror to our own consciousness, prompting us to ask if our capacity for art, science, and love is an anomaly or a universal phenomenon. Perhaps the most significant ethical implication is what the discovery would tell us about our own fate. The existence of a once thriving civilization, now dead, would be a monument to what could be our own end. This connects directly to the Great Filter theory. If we find that a Martian civilization fell victim to a planetary catastrophe, it would serve as a chilling warning about the fragility of our own existence. We would be a species looking upon its own potential past and a possible future. On a sociological level, the discovery would either unite humanity or exacerbate its divisions. Would the knowledge that we are not alone in the cosmos foster global unity as we prepare to face the universe together? Or would it ignite competition and conflict as different nations and groups vie for control and interpretation of the discovery? The question of who owns the discovery and the subsequent research would raise complex legal and political issues on an international scale. Beyond the philosophical and sociological implications, the discovery would raise complex ethical questions about our responsibility to the deceased civilization. Do we have a moral obligation to a species that is no longer here? Should we treat the Martian ruins as a sacred memorial, a cosmic grave that should not be disturbed? Or is our scientific imperative to learn and explore a higher calling? The decision to excavate, study, and potentially display their artifacts would be an ethical minefield. The discovery would also raise the question of our responsibility to ourselves. By studying what may have led to their demise, whether it was planetary decay, an asteroid impact, or a self-inflicted wound, we might be able to find the keys to our own survival. The ruins of a Martian civilization would be a silent judge of our own progress, a mirror reflecting our own potential to both create and destroy. Ultimately, the discovery of a past Martian civilization would be a moment of profound cosmic introspection. It would force humanity to confront its own mortality, its own purpose, and its own future. It would change not just our science, but our very understanding of ourselves. A silent conversation has been happening on Mars for billions of years, and the language is chemistry. The search for a past civilization or even just life is not about finding monuments or artifacts. Instead, it is a meticulous hunt for a biosignature, a chemical fingerprint that only life can leave behind. A biosignature is any substance, object, or pattern whose origin requires a biological agent. These are the subtle, durable clues that might have survived the death of the planet. The search for them is the very core of astrobiology. The search for biosignatures can be thought of in three categories, from the most definitive to the most ambiguous. Direct biosignatures. These are the holy grail, a perfectly preserved fossil of a Martian microbe, a strand of DNA or a Martian-specific protein. However, the chance of these surviving billions of years of cosmic and geological weathering is almost zero. Ambiguous but durable biosignatures. These are the most likely to be found and are the current focus of our missions. They are chemical and geological clues that, while not conclusive on their own, are strongly indicative of biological activity. Basic building blocks. These are the simple molecules and elements of life. While essential, their presence does not prove life, as they can also be formed by non-biological processes. The most compelling biosignatures we are looking for are those that are too complex to be easily created by natural processes, but are durable enough to have survived. Methane. The atmospheric anomaly, perhaps the most intriguing of all potential biosignatures, is methane. On Earth, the vast majority of methane in the atmosphere is produced by living organisms, particularly microbes. In 2004, the ESA's Mars Express orbiter detected trace amounts of methane in the Martian atmosphere, a finding that was later confirmed by ground-based telescopes and the Curiosity rover. The levels were minuscule, but what made the finding so compelling was that the amounts seemed to fluctuate seasonally and were concentrated in specific regions. While methane can also be produced by purely geological processes, such as the interaction of water with certain rocks, the seasonal fluctuations could hint at a biological source, perhaps microbes in a subsurface reservoir that become more active during the Martian summer. The ambiguity of this finding is a powerful driver of future exploration. Organic molecules. The building blocks. Our rovers are also hunting for organic molecules, the carbon-based building blocks of life. The Curiosity rover, in its exploration of Gale Crater, has discovered a range of complex organic molecules, including thiophenies and benzene, in ancient lakebed mudstones. While these molecules are essential for life, they can also be created by non-biological processes. The challenge is in the context of their discovery. Finding them in an ancient lakebed, a place that once held liquid water and was protected from radiation, makes a biological origin more plausible. Isotopic ratios, the smoking gun. The strongest chemical clue we could hope to find is a specific isotopic signature. Living organisms have a preference for certain isotopes of elements. For example, microbes on Earth prefer to use the lighter carbon-12 isotope over the heavier carbon-13 isotope in their metabolic processes. This preference leaves a distinct chemical signature in the rocks and soil. The discovery of a similar pattern in Martian rocks would be an incredibly powerful indicator of past life, as this kind of chemical preference is a hallmark of biology. The ultimate goal of the search for biosignatures is to find a confluence of evidence: methane plumes, organic molecules, and isotopic ratios, all pointing to the same conclusion. The Mars sample return mission is the final crucial step in this process. By bringing these samples back to Earth, we will be able to analyze them with our most advanced laboratory instruments, and finally, resolve the question of whether Mars was once a living world. We know that the vast majority of water on Mars today is frozen solid, locked away in the polar ice caps and in subsurface permafrost. However, recent discoveries have sparked a tantalizing debate. Could some of that water exist in a liquid state deep beneath the surface? This question is central to the possibility of present-day life on Mars, as liquid water is a fundamental requirement for life as we know it. The most compelling Evidence for a potential reservoir of liquid water came in 2018 from the European Space Agency's Mars Express orbiter. Using its Mars Advanced Radar for subsurface and ionosphere sounding MARSIS instrument, scientists scanned the planet's southern polar ice cap. The radar sends pulses into the ice and measures the returning echoes. The properties of the echoes reveal the nature of the material they reflected off. In a region of layered ice about a mile below the surface, the MARSIS radar found a very bright reflection, a signal that was far more intense than those from the surrounding areas. On Earth, this exact type of signal is the signature of liquid water, which reflects radar signals much more strongly than ice or dry rock. This finding was a monumental discovery, suggesting the existence of a subglacial lake about 12 miles across. The implications were enormous. Liquid water, and thus a potential habitat for life, could exist on Mars today. The water would be kept liquid by a combination of pressure from the overlying ice and the presence of dissolved salts, which act as a natural antifreeze, lowering the freezing point of the water. However, the scientific community is cautious. Subsequent studies have presented alternative explanations for the bright radar signals. Some researchers have suggested that the signals are not from liquid water at all, but rather from a geological process called constructive interference, where radar waves bounce off closely spaced ice layers in a way that amplifies the signal, creating a false impression of liquid water. Others have argued that the bright signal could be caused by certain types of clay or other minerals that are not wet but are highly reflective. The debate is ongoing, but in a separate and equally compelling discovery, an international team of researchers used a different method to find new evidence. They used data from NASA's Mars Global Surveyor to analyze the surface topography of the ice cap. They found subtle, kilometer-long undulations and depressions in the surface of the ice that match computer model predictions for how a body of water beneath an ice sheet would affect the surface. This provided the first independent line of evidence, using data other than radar, that a body of liquid water could exist beneath the ice. While the debate over the polar lake continues, a new and even more significant discovery was made using data from NASA's InSight lander. Its super-sensitive seismometer detected thousands of Marsquakes and meteorite impacts. By analyzing how the seismic waves from these events traveled through the planet's crust, scientists discovered a large, low-velocity layer between 5.4 and 8 kilometers below the surface. They found that a significant amount of the seismic waves had passed through rock that was saturated with a fluid. Their calculations suggest that the amount of liquid water trapped in the pores of these fractured rocks could be enough to fill a global ocean, more than half a mile deep if it were to cover the entire planet. This finding is a strong indication that Mars, despite its dry surface, may be holding a vast reservoir of liquid water deep within its crust, a true missing ocean from its watery past. The existence of any liquid water on Mars today, whether a small subglacial lake or a vast underground aquifer, has profound implications for the search for life. It provides a potential habitat, a protected environment away from the brutal surface radiation and temperature extremes. On Earth, we find life in the most unlikely of places, including deep beneath the Antarctic ice sheets and in subterranean aquifers where organisms thrive in total darkness. The same could be true for Mars. While these potential reservoirs of water are difficult for our current rovers to reach, they provide a powerful motivation for future missions. The search for a past Martian civilization is not just about a ghost. It is about finding a sanctuary, a last bastion of life that may have survived the planet's death, patiently waiting for us to find it. For a time, humanity's fascination with Mars was a romantic one, filled with fantasies of ancient, dying civilization. Today, that narrative has shifted and our fascination has become a practical one. We no longer just dream of finding an ancient Martian civilization. We are actively planning to create our own. This ambition, the colonization of Mars, is arguably the most significant project in human history and will be our species' ultimate legacy. The plan to colonize Mars is no longer science fiction. It is a multi-decade, multi-billion-dollar endeavor being pursued by both government agencies like NASA and private companies like SpaceX. The timeline is ambitious, with initial crewed missions being targeted for the 2030s. The long-term vision is to establish a self-sustaining colony, a settlement that can survive without constant resupply from Earth. This migration will happen in stages. Initial cargo missions. The first ships to Mars will be unmanned, carrying the essential supplies for a future colony. Habitats, life support systems, power generators, and equipment for resource extraction. The first human outpost. A small crew of astronauts will arrive to set up the foundational outpost. Their mission will be to lay the groundwork for a permanent presence, which will be a Martian frontier of sorts. The self-sustaining colony. Over decades, the colony will grow from a small outpost to a true self-sufficient city. It will involve a mix of humans and advanced robotics, with the ultimate goal of achieving a population of over 1 million people. Life on Mars will be an immense challenge, forcing humanity to develop new technologies and a new way of living. Habitats and life support. Colonists will live in specially designed habitats, such as underground lava tubes or geodesic domes, which will protect them from the harsh radiation, temperature extremes, and thin atmosphere. Resource utilization. The key to survival will be living off the land, a process known as in situ resource utilization. Mars's atmosphere is rich in carbon dioxide and its poles hold vast reserves of water ice. Colonists will use this to produce rocket fuel, breathable air, and water for drinking and agriculture. A new society. A Martian society would be a new kind of civilization, one built on the principles of sustainability and cooperation. The isolation, the shared purpose, and the unique challenges of living on a new world would forge a new culture with its own social norms, art, and identity. A Martian civilization would be a new branch on the tree of human history. The colonization of Mars is not just about science or adventure, it's about the survival of our species. The Earth is a fragile place, and a single global catastrophe such as an asteroid impact or a self-inflicted nuclear war could lead to the extinction of humanity. By becoming a multiplanetary species, we would be creating a cosmic backup of our civilization, ensuring the long-term survival of human consciousness. In a curious twist of fate, the search for an ancient civilization on Mars has led us to the most profound realization of all. The history of Mars may be our own legacy. We may never find the ruins of a past civilization, but in a few decades, we will begin to create our own. A new civilization built on a world of dust and rock. A monument to the endurance and ambition of the human spirit. Our exploration of Mars, so far, has focused on two distinct, yet interconnected, searches: the hunt for microbial life and the hunt for a technological civilization. These are often discussed together, but they are fundamentally different quests with their own unique challenges and goals. Understanding the difference is crucial to appreciating the true complexity of the search for life in the cosmos. The search for simple, microbial life is rooted in a core principle of astrobiology. That life, in its most basic form, is a natural and perhaps common outcome of planetary evolution when conditions are right. We've seen that early Mars had a favorable environment, liquid water, energy sources, and the building blocks of life. Our missions, therefore, are designed to find biosignatures, the chemical and geological fingerprints of life's presence. We look for organic molecules in ancient lake beds, we analyze isotopic ratios, and we search for geological formations like stromatolites that could only be created by microbial activity. This search is a methodical, patient, and scientific one. It's an exploration guided by the principle: that if life exists beyond Earth, it is most likely to be microscopic, because on our own planet, microbial life dominated for billions of years before the first complex organisms appeared. The discovery of even a single microbe on Mars, a second genesis, would be one of the most monumental findings in human history. It would prove that life is not a cosmic fluke, but a universal phenomenon. The search for intelligent, technologically advanced beings is a completely different endeavor. It's a hunt for techno-signatures, which are any measurable property or effect that provides scientific evidence of past or present technology. This is the realm of grander-scale evidence, abandoned structures, industrial waste, artificial light, or, most famously, electromagnetic signals. This is the domain of SETI, the search for extraterrestrial intelligence, and its application to Mars. The logic behind this search is built on the assumption that intelligence is not an inevitable outcome of life. On Earth, it took over 4 billion years for a single species to develop the ability to build technology and communicate with the stars. This suggests that the step from simple life to intelligence is incredibly difficult and rare. The Fermi paradox, the silence of the cosmos, is a testament to this possible rarity. On Mars, these two searches are conducted simultaneously. Our rovers look for biosignatures, trying to answer the question of whether Mars was a living world. At the same time, orbiters scan for techno-signatures, searching for any sign of a technologically capable civilization. The difference in the search is profound. Finding a fossilized microbe would tell us about life's potential, but finding an ancient technological artifact would tell us about intelligence's destiny. The first would prove we are not alone in the universe. The second would be a mirror to our own future. The search for microbial life is a quest for a biological commonality. It is about understanding the cosmic rules that govern the emergence of life. The search for a Martian civilization, however, is a quest for an improbable rarity. It is about understanding the ultimate fate of a species that gained consciousness. Ultimately, we are a species driven by both questions. We want to know if life is common, and we want to know if intelligence is common. The red dust of Mars may hold the answer to both, and the journey to find it is a journey of two different, yet equally profound, searches. The search for a past Martian civilization, one that is no longer there, leads us to a fascinating and unsettling possibility. What if they aren't gone at all? What if a technologically advanced civilization, seeing its planet begin to die, did not perish but simply left? This is the core of the Silent Watchers hypothesis, a theory that suggests a highly advanced Martian society might have left their world long ago and are now observing us from afar, like distant caretakers of a cosmic garden. The idea is rooted in a simple question. For a species with the technology to build cities and a presence on a dying planet, why not just leave? The journey from Mars to Earth is a short one in cosmic terms, and a civilization with advanced spaceflight capabilities could have made the trip in a matter of months. This theory presents a compelling solution to the paradox of Mars's silence. The planet isn't a graveyard, it's an abandoned homestead. Once they arrived in a new location, perhaps on Earth, a Martian civilization would have had to make a profound choice. Would they reveal themselves to humanity, or would they choose a path of silence and observation? The Silent Watchers hypothesis, a variation of the more famous zoo hypothesis, suggests that they would have chosen the latter. This theory proposes that advanced civilizations, having reached a certain level of maturity, deliberately avoid contact with less developed species, treating them like animals in a nature reserve. This non-interference policy is designed to allow the less advanced species to develop on its own, without any outside influence that could distort its natural evolution. This hypothesis offers a compelling explanation for the many mysteries that have captivated us. The lack of any definitive, unambiguous evidence of a past civilization on Mars is not a sign of absence, but a testament to how thorough their departure was. The geometric anomalies and peculiar objects we have found could be the rare, long-forgotten artifacts that were not fully erased. The sudden leap in human consciousness, art, and technology could be the result of a subtle, guiding hand, a gentle nudge from the watchers who are silently observing us. The silent watchers hypothesis also provides a chilling explanation for the silence of the cosmos. The Fermi paradox, which asks why we haven't found any evidence of other intelligent life, is not a paradox at all. It is a sign of a universal rule of non-interference. We are not alone in the cosmos. We are simply being watched patiently from afar. The search for a Martian civilization takes on a new meaning in the context of this hypothesis. Our rovers, in their search for life, are not just exploring a dead planet. They are, in a sense, a cosmic message to the silent watchers. The fact that we have developed the technology to reach their former home is a sign of our own progress. Our search for a past civilization is a test of our own intelligence, a puzzle left for us to solve. The silent watchers hypothesis is, for now, purely speculative. But it is a powerful idea that transforms our cosmic isolation into a profound state of being watched. It asks us to consider whether our own journey is being guided and whether our own future is being observed by the silent, patient, and distant eyes of a civilization that once called Mars home. The search for a Martian civilization is, in a sense, a localized test of a much grander question. Are we alone in the universe? When we look out at the night sky, we are gazing upon a cosmos of staggering scale. Our own galaxy, the Milky Way, contains an estimated 100 to 400 billion stars. The observable universe, in turn, contains billions of galaxies. This immense, unfathomable vastness is the basis for a powerful statistical argument for the existence of life elsewhere. This argument is best articulated by the Drake equation, a probabilistic formula developed by astronomer Frank Drake in 1961. The equation is not meant to provide a single, definitive number, but rather to be a thought experiment, a way to organize our ignorance and guide our search. It attempts to calculate the number of active, communicative extraterrestrial civilizations in our galaxy at any given time by multiplying a series of factors. The equation is as follows. R epini full fifths m. Let us break down each component, and in doing so, we will confront the immense unknowns of the cosmos. Doodles, the rate of star formation. This is the most well understood factor. We know that stars are born at a relatively steady rate in our galaxy, about 7 to 10 per year, .fp, the fraction of stars with planets. When the Drake equation was first formulated, this was a complete guess. Today, thanks to missions like the Kepler Space Telescope, we know that the answer is remarkably high. The data suggests that nearly every star in the galaxy has at least one planet. These first two factors, once pure speculation, now provide a solid foundation for the statistical argument. With hundreds of billions of stars and each with a high probability of having planets, the sheer number of possible worlds is staggering. The next factors, however, are where the numbers become deeply uncertain and where the great filter theory comes into play, DENT-NI, the number of planets per star that are in the habitable zone. This is the Goldilocks factor, the number of planets that orbit their star at a distance where liquid water could exist. The number of confirmed planets in the habitable zone is growing rapidly, with a conservative estimate of 1 per 5 stars. This means that our galaxy alone could contain billions of potentially habitable worlds. FL, the fraction of habitable planets that actually develop life. This is the first major unknown. We have only one data point for this factor: Earth. If life is a natural outcome of planetary evolution, this number could be close to 1. But if the leap from non-life to life is a cosmic rarity, this number could be infinitesimally small. Our search for a Martian microbe is a direct attempt to answer this fundamental question. Phi, the fraction of life that develops intelligence. This is the most profound and humbling factor. It took over 4 billion years for a single species on Earth to develop the ability to ask this very question. We have no way of knowing if this is a common occurrence or an extreme rarity. FC. The fraction of intelligent civilizations that develop a technology to send detectable signals into space. This factor assumes that a civilization would choose to communicate. It's possible that all intelligent civilizations choose to remain silent, or that they only use non-electromagnetic forms of communication. L. The length of time those civilizations release detectable signals into space. This is the final and most chilling factor. If a technological civilization lasts only a few centuries before destroying itself, the chance of us hearing from them is vanishingly small. This is the heart of the Fermi paradox. The universe's vastness, when viewed through the lens of the Drake equation, is both a source of hope and a cause for profound loneliness. The statistical argument for the existence of life is powerful, but the search for a Martian civilization may hold the key to understanding the great unknown factors in the equation. A finding on Mars could tell us whether the transition to life and intelligence is a common occurrence or a cosmic miracle, and in doing so it would inform our place in the universe. Science fiction and imagination are not just forms of entertainment, they are the engines of scientific inquiry and exploration. While a scientist's work is grounded in data and observation, the initial spark, the hypothesis, the grand question, and the vision of what is possible often comes from a place of pure imagination. The search for a Martian civilization is in many ways the ultimate example of this symbiotic relationship between fact and fantasy. Throughout history, science fiction has served as a visionary blueprint for future technological advancements. Long before they were scientific realities, concepts like the atomic bomb, rockets to the moon, and global satellite communication were first imagined in the pages of fiction. In the late 19th century, authors like Jules Verne wrote about voyages to the moon, and in the early 20th century, H.G. Wells imagined alien invasions and time travel. These stories were not just speculative, they were a way of thinking about what could be possible, pushing the boundaries of what was considered achievable. The influence of science fiction on real-world space exploration is undeniable. Many of the greatest minds in space exploration cite science fiction as a pivotal influence in their careers. Carl Sagan, a key figure in the search for extraterrestrial life, often spoke of his fascination with Edgar Rice Burroughs' Mars books. The Star Trek series, with its depiction of advanced technology and a hopeful future, has inspired countless individuals to pursue careers in science and engineering. The International Space Station and even the flip phone are just a few examples of real-world innovations that were directly inspired by science fiction. The search for a Martian civilization is fundamentally a quest.
Fueled by a simple question: what if?
It's a question that scientific data cannot answer on its own. It's the what if that makes us look at a rock and wonder if it was a tool, or to look at a geometric formation and wonder if it was a building. This imaginative leap is a vital part of the scientific process. It's what drives us to propose new theories, to design new missions, and to develop new instruments to test them. The face on Mars, while ultimately a product of pareidolia, is the perfect example of how this works. The outlandish theory that it was an artificial monument captured the public's imagination, which in turn generated funding and support for the very missions that ultimately debunked it. Without the speculation, the science might not have advanced as quickly. The search for a Martian civilization, therefore, is not just a scientific endeavor. It is a profound human one, an act of dreaming that is being realized through the slow and meticulous work of science. The transition from science fiction to science fact is a continuous cycle. The imaginative stories of one generation become the scientific goals of the next. Today, concepts like terraforming Mars, a planetary-scale engineering project, are no longer confined to the pages of books. They are now being discussed and studied by scientists and engineers at NASA and other space agencies. Our current aspirations to establish a human, colony on Mars are a direct continuation of a conversation that began decades ago in the minds of science. Fiction writers, the role of imagination in scientific discovery is to provide the initial spark, to create the grand vision, and to inspire the next generation of explorers. The search for a Martian civilization is a testament to this power. It is a quest that is driven by our need to know, but it is made possible by our capacity to dream. For all our technological progress, our countless rovers, and our meticulous scientific analysis, Mars remains a world of profound and enduring mysteries. The more we learn, the more we realize how much we do not know. The Red Planet is not a static graveyard, but a dynamic and secretive world that holds the keys to some of the most fundamental questions we can ask about our place in the universe. This is the greatest question of all. We have established that early Mars was a habitable world with liquid water, energy sources, and the chemical building blocks of life. But did life ever arise? Our search for biosignatures, from the puzzling methane plumes that fluctuate seasonally to the complex organic molecules found in ancient lake beds, has provided tantalizing clues but no definitive proof. If the Mars Sample Return mission were to find evidence of ancient microbes, it would be a monumental discovery. But what if it finds nothing? The question would remain, why did a habitable world fail to produce life? A related question is whether life could exist on Mars today. While the surface is inhospitable, we have evidence of vast reservoirs of water ice and perhaps even liquid brines in the subsurface. Could hardy extremophile microbes be eking out an existence in these hidden oases? The underground hypothesis suggests that if life exists, it's not on the surface, but in a protected subterranean refuge. This is a question we are only just beginning to explore. We know that Mars was once a water world, but where did all that water go? While the general theory points to the loss of its magnetic field and the subsequent atmospheric stripping by solar winds, the specifics are still debated. What was the exact timeline? Was the water lost slowly and steadily, or was it a series of cataclysmic events? How much of the water was lost to space and how much is still locked away in the planet's crust? Some theories suggest that a vast, ancient ocean could be trapped in the porous rock of the Martian interior, a geological ghost of a past that we are only just beginning to comprehend. The answer to this mystery is not just about Mars. It's about the fragility of planetary climates. This is the most profound and chilling of all the mysteries. If life is a common occurrence in the cosmos, why have we found no definitive evidence of a civilization on Mars? This is the Fermi paradox applied to our own backyard. Is the silence of Mars a sign that the Great Filter, a barrier to the rise of intelligent civilizations, is ahead of us? Did a potential Martian civilization die in a planet-wide cataclysm, or, more terrifyingly, did it self-destruct? The search for a Martian civilization is, in many ways, an act of looking for a warning about our own future, a cosmic mirror of our own potential fate. Even the most basic features of Mars are filled with mystery. Its two tiny, lumpy moons, Phobos and Deimos, have baffled scientists. Their perfectly circular orbits suggest they are not just captured asteroids, but their odd shapes defy conventional theories of moon formation. The stark contrast between the smooth northern plains and the heavily cratered southern highlands is also an enduring puzzle. The leading theory is a single, immense asteroid impact, but the scale of the required impact is staggering. Mars is a world of unanswered questions, and our mission is to find them. We explore Mars not just to find answers, but to learn how to ask better questions. The journey to the Red Planet is a journey into the unknown, a cosmic mystery that will continue to fuel our curiosity for generations to come. For over half a century, we have sent silent robotic emissaries to Mars. They have taught us that the planet was once wet, that its climate collapsed, and that its dust hides no clear secrets of a past civilization. But the quiet curiosity of our robotic era is now giving way to a new, more ambitious phase of exploration, one that will fundamentally change our relationship with the Red Planet. The search for a past civilization is becoming a quest to build our own. The immediate next steps in the ongoing quest for Mars are a mix of completing our current missions and launching new, more ambitious ones. The Mars Sample Return Mission, an unprecedented international collaboration between NASA and the European Space Agency, is the single most important project in this new phase. Our Perseverance rover has already collected dozens of rock and soil samples from an ancient river delta, and the next step is to retrieve them. This multi-billion-dollar mission will send a lander and a small rocket to Mars, which will launch the samples into orbit, where they will be captured by an orbiter and brought back to Earth for analysis. This mission is the scientific gold standard, as it will allow us to use the full suite of our most advanced labs to finally search for a definitive answer to the question of past life. Beyond that, the ExoMars program, a collaboration between ESA and NASA, will send the Rosalind Franklin rover to Mars. This rover is designed to drill up to 2 meters beneath the surface, a depth that is critical for searching for life. Any microbes that might have survived Mars's hostile surface environment would almost certainly be shielded by rock and soil, and the Rosalind Franklin rover is equipped with the tools to find them. Other missions are being planned to study the Martian moons, Phobos and Deimos, in greater detail. Japan's Martian Moons Exploration (MMX) mission will return samples from Phobos, which could provide crucial clues about its unusual origin. But the most profound shift in the ongoing quest is our preparation for human exploration. NASA's Artemis program, while focused on the Moon, is a critical stepping stone to Mars. We are using the Moon as a proving ground to test the technologies and life support systems that we will need for a journey to the Red Planet. This includes learning to harvest water from lunar ice, a skill that will be vital for making fuel and water on Mars. Private companies like SpaceX are at the forefront of this effort, with plans to build fully reusable rockets that can transport humans and cargo to Mars. Their ultimate goal is not just to send a few astronauts, but to build a self-sustaining city, a new civilization on a new world. To achieve this, we are developing a series of revolutionary technologies. In situ resource utilization, SRU. This is the ability to live off the land on Mars. NASA's MOXIE instrument on the Perseverance rover is already demonstrating this by converting Martian carbon dioxide into oxygen. This technology will be essential, creating breathable air and rocket fuel for the return journey. Nuclear propulsion. The 9-month journey to Mars is a major challenge due to the immense exposure to radiation and the psychological stress of isolation. New propulsion technologies, such as nuclear thermal propulsion, which use a nuclear reactor to heat and expel a gas, could cut the travel time in half, making a human mission more feasible and safer. Artificial intelligence and robotics. Given the communication delay between Earth and Mars, future missions will rely heavily on autonomous robotics and AI. These robots will be capable of building habitats and mining resources without human supervision, laying the groundwork for a future colony. The search for a past Martian civilization has led us to the most profound realization of all. The history of Mars may be our own legacy. We may never find the ruins of a past civilization, but in a few decades, we will begin to create our own. A new civilization built on a world of dust and rock, a monument to the endurance and ambition of the human spirit. And with that final thought, our quiet journey across the cosmos comes to an end. If you found this exploration of Mars's mysteries soothing and thought-provoking, please consider supporting Tierra Hueca. A quiet like, a gentle subscription, or a comment sharing your thoughts helps this cosmic conversation reach more curious minds. Sleep well, traveler.